Hello again, folks. Today I'm going to be doing section 2.5 and 2.6, which is more practice in solving equations, just equations that are a bit more sophisticated than linear type. Anyhow, that is again according to our schedule, which if you need to, you can always look up on Canvas, or I do zoom in on you like that. This is what we had covered on Tuesday, and again, sticking with a regular schedule of Tuesday and Thursday. The sun is bleeding through a little bit, but section 2.5 and 2.6 is what will be covered today. It might be long as I was preparing for this. It just seemed like a lot stuffed into one day, but it's what we have to do for an abbreviated semester, because it's fall too. Anyhow, the packet that I have prepared for you today looks like this. All right, it's about 8 pages. All right, and it's a summary of the material that I'm going to be discussing. This is an overview of methods for solving quadratic equations. All right, specifically. Basically, if you have the linear, the basic skills of performing opposite operations down, then the next logical thing is solving quadratics. It's 1 degree higher. And anything that follows it might be some derivative of that. All right. This, just to give you an overview of different factoring techniques. All right. Verbal description, if you will. A strategy. Given any size polynomial, you might try factoring by a Monomial Gcf. All right. If you have a 4-term wide polynomial, you might try factoring by grouping. All right, and then there's increasing with decreasing sizes. Right, that's more of a verbal description. Here's a visual description. This is also an overview, but this is an overview of factoring. The 2 basic techniques are here and here. These are models that basically you follow. Right, you might identify a trinomial as the perfect square trinomial specifically. Right, or the difference of 2 squares, in which case it would factor like this. Nearly identical except for the signs. The hardest to memorize, of course, is the sum of difference of 2 cubes, right? But it's easy to designate or identify because it has exponents of 3, right? And there is a mnemonic. This is what it is. SOAP is the signs. Same as the original thing, opposite, always positive. Okay, here is a list of perfect squares and perfect cubes that in the long run you would want to memorize these. When you see these numbers 1, 4, 9, 16, 25, a little alert should go off in your head and go, they're squares. All right, why when you're factoring? This is more or less the same thing from the opposite perspective. Instead of squaring, square root, cube root, and 4th root. If you are given a number like this, square root of 1, you could write it as 1 squared. And then the opposite operations would cancel. If you're given a number like 36, you could write it as 6 squared. And if it happens to be underneath a radical, then it would just be 6. All right. Here's a strategy for factoring radicals. Here is the difference between something that's written in notation, radical notation versus rational notation. Right? These are the same quantity, basically, but in 2 different styles. Right? Not to be confused with rational equations. All right? This is a number that has been written in rational notation, a style of writing. Okay? And a brief description of that. This is just a summary of rules of exponents, the product rule. How you would combine the exponents if you were multiplying like bases, or if you were dividing them. And that's it, right? Good to have this on hand, all right, as I'm doing some examples, because I'll be referring to it a lot anyway. But while you're doing your assignments in My Open Math, all right, you don't have to go dig into a textbook or anything like that. Pretty much everything that you need to know is in this packet. Okay? And that's available in Canvas pages. I'll give you the link naturally. Okay? All right. see what I can get done. I'll try not to go more than 3 hours. I think it might be at least 2.5. We'll see. Okay, section 2.5 is about solving quadratics firstly, and 2.6 is some other types of equations. So rather than take up my limited real estate here, I'm just going to refer to the section number, and let me give you an overview. All right. To this point in the conversation, we've discussed really 1 or 2 types of equations. And primarily the linear type. I alluded to the quadratic type, I believe, last time, but I certainly didn't go into techniques, because that's the subject of today. All right. How to identify these? All right, pretty easily. Basically, it's not, the variable isn't always x, of course, but if that is the variable, all right, look for the exponent. All right, these are degree 1, all right, and quadratics would be degree 2. And in theory, if you had a cubic equation, it would be degree 3. Okay. So look for the exponent that is attached to the variable. It's usually an x, not always, but typically. It's either x to the first, which would, is optional. They don't always write that. But then higher than 1, they would have to. Right? So they will put 2. Okay. Okay. Now, as for what you do in a situation like that, if we had this as part of some more complex expression here, other than just x, and this is just arranged for the sake of simplicity that it's set equal to 0. All right? You go about the process of solving this via basic techniques. All right? And the basic techniques are, you try to simplify first, of course, as a preliminary step. But basically, opposite operations. That is, if you see adding, you subtract to move something over the equal sign. If you see multiplication, you divide. Right? Barring some situation where you have fractions, and you know that when you divide fractions, you end up having to multiply by reciprocal. That's something that more or less predates, the subject of algebra. That's arithmetic. But pretty much what you see, you're going to do the opposite. So if you see addition, you're going to subtract. If you see multiplication, you're going to divide, and vice versa. All right. When it gets to quadratics, again, just to amp this up a little bit, something a little bit more interesting than just x squared. Say that you had this, ax squared plus bx plus c, which incidentally has a name. This is called the standard form of a quadratic equation. And I can't stress that last point, that the operative term there is equation. You might have seen or heard of quadratic functions, which is a topic a little bit further down the pike for us. It's funny because they don't call the arrangement of the terms when you're dealing with functions standard. They call it general when it looks something like that. They reserve the word standard for something that is alternatively referred to as the vertex form. Anyway, I hate that. All right, I don't think that people should be inconsistent with the labeling, especially math people. All right, but when you're talking about an equation rather than a function per se, this is referred to as the standard form. And the reason that it is good to recognize is because it's very useful either when you're trying to graph something, to use your calculator to help you, or if you're trying to factor, right? Or maybe if you're going to use the quadratic formula, which is incidentally those methods that you would use that are a little bit more sophisticated than just opposite operations, right? In general, right, the kind of go-to technique for solving a quadratic equation, at least if it's arranged this way, and you will make it arranged that way, is to factor. And when something can't factor, then what you might try is, well, firstly, the square root property. But that isn't necessarily a situation where you can't factor. Well, those situations that you can't factor, right, you might try graphing, which is kind of cheating a little bit, and completing the square, which is to take something that is otherwise not factorable, for lack of a better word, and making it factorable. And then lastly, there's the swat and the fly with a bazooka, which is the quadratic formula. That's really squeaking it in there, right? Sorry, this is out of the frame. Anyhow, this information that I am referring to is basically on this piece of paper. All right, and I'll show you how to do these, or how to use them. All right. How to do these. All right, anyhow, the quadratic formula is something that in theory would work whether you, for virtually any type of quadratic equation. If you are no higher than degree 2, you can use the quadratic formula, but it might be more trouble than it's worth, which is why I say it's kind of like swatting a fly with a bazooka. All right, it would get the job done, so to speak, but it might be overkill. All right, it's also not very nice. All right, okay, so this is where we're at for section 2.5, just the techniques for quadratic equations. This is section 2.5. Okay, let me move this out of the way. And I'll try not to destroy my board today. Alright, it's kind of purposely confining myself so that I could get away with not erasing. Which, incidentally, I should get a paper towel. And judging by how much alcohol I have in here, I get away with that. Okay, alright. Let's try graphing technique. I would guess that this probably works for anything as well. It's kind of cheating, alright, but the skill of using a calculator, I mean, it's cheating in the sense that you are avoiding or circumventing the task of being able to do something by factoring, which in the long run is probably faster, alright. But anyhow, if you look at your calculator, all right, your graphing calculator in theory, as I had mentioned in last class, all right, for how to graph, there's two buttons on the calculator, y equals, which allows you to enter things, all right, to graph, and then the graph button, which draws things. These other buttons that are here are for more specific purposes. Basically traces if you want to try to read the graph with the cursor. All right. Zoom is basically changing the screen dimensions, right? And window is also changing the screen dimensions, but more brute force. If you think about it this way, window is like the manual transmission, and zoom is the automatic. All right. Most people prefer to use the zoom. All right. Then there are these things in blue behind it, specifically calc. If you want to engage those features, you would hit the second button and then hit trace to get calc. All right. Well, in some cases, you would like to hit the table as well. The calc feature will tell you what the value of x will be if you rig the calculator first. All right. Here's what I mean. Make sure my thing is functional. Looks like it's okay. Boy, I'm going to be sad if after 3 hours that my camera's broken. Jeez, please, I hope that never happens. All right, here's an example. X squared. Let me put this as such. This will be an example of graphing to get the answer. Graphing to solve for x. Given x squared minus 6x minus 16 equals 0. Now, it's not always this nice that you have something already arranged in standard form, right? But if it's not given to you in standard form, purposely arrange the parts, right? One of the things that I included on this sheet again is this box to explain it. You'll see this box here, this box here, this box here, this box here, this box here. That's the shape, basically, that you want your equation to be in before you attempt any of these methods, right? It's more or less the ideal situation. So if you're going to graph, notice that you have all of the interesting stuff on one side, and you just have y on the opposite side. There is no y in this, right? Because it's not a two-variable graphing equation to start with. We're just going to try graphing to more or less cheat to get the answer. Right? So what we'll do is we'll just simply call this y, right? And that will rig up basically arrange the situation so that if y is 0, then what we're looking at are x-intercepts. Right? The solutions will be x-intercepts, otherwise known as zeros. Okay? So the next thing is that you're going to go into that feature on your calculator, y equals, right? And then immediately after that, hit the graph button so that you see what you get. The reason that you might do that first is because if it doesn't draw a picture, that just means that you have to adjust the screen dimensions somehow, all right? So I'll do that really quick, all right? In here, I'm gonna hit y equals, if I turn on my calculator first would be great, okay? Y equals, all right? Notice that I have a bunch of blank spaces to enter. Make sure that your plots are off as well. That means that they're not highlighted. If you have to, you can go up to here and then hit the enter button, and that will unhighlight something. All right. Anyhow, you're going to try to basically enter this, just the half that goes up to y. All right, x squared minus 6x minus 16 specifically. You don't hit y because it's already there. All right. Anyhow, if you want to enter x's easily, notice this button here that says x tau theta n. All right. Right out of the box, it's preset to give you x's. The only time that it would change to one of these other letters here, all right, is if you change the settings of your calculator. You won't have to worry about that. If your calculator is screwed up by any chance, all right, there's a key sequence you can go through to reset it, but the easiest thing, I hate to say it, is probably to slap the batteries out of it, wait a minute, and then put them back in. All right, and that will go back to factory settings. It's not very elegant to do that, but it would work. All right, so first term is x squared, so I'm going to hit x and then square here. Alternatively, you can hit this upward pointing arrow here called caret. All right. Now, there is one finicky thing about these calculators. It doesn't understand that minus and subtraction symbol are basically the same thing. Every other software program I've ever seen doesn't have a problem with that, but the TI-84 and 83 do. See this negative here? Don't use that. All right. Unless you're starting with a variable at the front, a coefficient at the front like 3, and you want to make it a negative 3, then use this, right? If you're going to try to just get a subtraction symbol, use that, okay? 6x minus 16. What you enter should look like this, basically, all right? Now you press graph, all right? Again, if all goes according to plan, you basically see the graph. Now, if you've had any experience with quadratics, you know what type of graph that they would make. If you just had something as simple as y equals x squared, as opposed to what I've created here in place of 0, y equals x squared minus 6x minus 16, the graph makes a parabola. And the parabola is kind of a hybrid V-U shape. It's really neither of those things, but it has some similarities, if that was its mother and father, if you will. All right. Parabola. Kind of a hybrid UV shape. All right. So, and it has a point that's famously referred to as the vertex. All right. He's curved this way, he's curved this way, barring some other alterations to that basic function. Anyhow, it's normally up sitting on the horizontal axis. In the drawing that you see here, it's a little bit narrower and it's kind of off the screen. I would leave it alone because you really don't care about anything else except the X-intercepts. And you have the X-intercepts already in the drawing. And if you wanted to, all right, you could just eyeball it and go, oh, I count the increments, and then you can get it without any issue. I have found that the trace feature, although it is nice, is not too reliable. Let me see. You see that little cursor there? It looks like a little bug to me, like a Spidey tracer. All right, it's never really right where you want it. Right? You could kind of guess that if it's a decimal of negative 2 point something just above the line, and negative 1.9 just below it, that it's probably whole number 2, but that's not really, I don't feel confident ever just guessing like that, and there's nothing you could do about it. That's the precision of this calculator. What you can do is one of two things. You could make the educated guess that it's 2, and then simply press 2, and then hit enter, and if it spits out, pardon me, I hit the wrong button here. Negative 2, backwards here. And if it gives you a 0, then you made a good educated guess. In fact, it is the y-intercept, negative 2x, 0y. Always 0 for the y, because that's where it started, right? And because it's literally an x-intercept. We've made it that, right? It's otherwise known as zeros. Rather than do that, all right, what you can do is go through this sequence. Once you have the picture, and we basically have this, we don't have just a regular parabola sitting up here in this more or less normal situation. We have it kind of off screen. Yes, you could adjust the dimensions of the screen if you like, but we're not after that, at least not right now. We have what we can see are 2 zeros, 2 x-intercepts. It makes sense, because if you have something that's not a straight line, if you have a curve like this, that if it's just a little bit lower than where it would normally be, it's going to cross the x-axis in 2 places. Right. This is an x-intercept. This is an x-intercept, where I put the dots. And again, you could eyeball it if you had to, but I wouldn't. All right. What you will do, if you want the calculator to definitively tell you, it's a bit of an arduous process, but you can get it to work, is this. Once you have the drawing, hit second, and then trace. And this will engage the calc feature. Right? In the calc menu, you're going to see something that literally says 0. You know? Since an x-intercept is otherwise referred to as zeros, that's the option that you want to explore. Now here's the part that I find kind of personally annoying, but here, I'll go through the process with you. You hit second, and then you hit trace to get the calc. Notice that the option is 0. Incidentally, if in the menu you have missing things different from what I have, that probably just means that you need to update the software on your calculator. There's 2 ports here, all right, as long as you have the wire, all right, that if you go to the TI website, all right, and you connect it via USB most likely, all right, you can have your software updated for free, right? You got to dig for it a little bit, right? And it might take a while, especially like if your calculator is old. Mine is like 15 years old, so it took about an hour or 2 to update. Anyhow, you could choose 2 or you could scroll down to it. It's going to ask you hokey questions. It's going to ask you weird things like left bound, and then you'll see right bound, and then you'll see the question of guess. Left bound and right bound are asking you to tell the calculator, where do you want me to look for the answer? All right, where do you want me to read from? Left bound means don't look any further towards the left, right? And right bound means don't look any further than the right. You're narrowing its perspective for it, right? what that amounts to is basically this. Left bound is, in our case, slightly above the axis, so like that. So okay, don't look any further left than that. It's a little counterintuitive, I suppose. Then you hit enter, and then it asks you the same kind of question. Right bound, how far to the right do you want me to look? Just underneath this point. Which I have to use this arrow. No, the other way. There you go. See, just underneath the arrow, then you hit enter. And then you hit enter again. Because again, it asks you, you want me to guess? And you go, yeah! Why would I bother asking you? All right? And it gives you an educated guess. -2, 0. Same as if you read it yourself and went, well, it's probably a whole number, right? Not that it always is, but you would guess that. Well, it actually is a whole number. It told you. When y is 0, that's what x is in this location, all right? You can go through the same process over here, but you have to do the same key sequence. You have to go through second, trace, hit calc, and then choose 0. All right, and then tell it left bound, right bound, and guess. Right. Left bound is, again, usually just above, right, on the very far left, right, or just, you know, it depends on the situation really, but it's either just above or just below the axis. And then the same situation, but the opposite, right, depending upon the graph, for right bound. It's either just above or just below the drawing, right? Again, it's like putting blinders on a horse. You have to tell it where to look, you know? Anyhow, this location is -2, 0. That's what the x value is. So that's one of the solutions for x. X is equal to -2. What's this one? You can, again, try to eyeball it and count the increments, right? Or go through the process again, all right? I'll do it with you, all right? So you hit second, and then you hit trace to get calc. And you hit 0 again, 2. And now you have to, unfortunately, move this cursor all the way over here, which means that you're gonna have to go zipping or doing over there. Zip, zip, zip. Zipping the modern way. And it disappears for a while. There it goes. Okay, and since now you're on this side, the left bound is, again, just above the line. All right, that's how far to the left that you want to look. Hit enter, and then you go just underneath it, and you notice an arrow showed up here. And you go, okay. And it says, you want me to guess? And you go, yeah. All right, and then it tells you, it gives you an error message, of course. Jerky thing. All right. Sorry, I think I befuddled it, so I'm gonna do it from scratch here. Left bound. Like that. Calculator's not that smart, unfortunately, and neither am I. All right, so I shouldn't be throwing mud here. Guess, please, yes. Why is it giving me an error message? If it gives you a hard time, there's some conflict somewhere, all right? I'm gonna turn it off and then turn it back on. That's how sophisticated I am, all right? There's my equation. This highlighted equals means that it's been drawn, all right? All right. Hit graph, and I have that. And now I'm back to square one. Doing this backwards is probably not helping me. So left bound. Oh, that's why. Because from my perspective, and I'm looking at the mirror image on my computer here, all right, the camera that's shooting this video is backwards for some reason while it's shooting, all right? Anyhow, that is the left bound. So there's a conflict of logic here. That is the left bound as it is. So I'm gonna go yes. And now just above is the right bound. And then go guess. And there you have it. At 0 over here, all right, x is 8. Okay. So you got 2 answers. That's usually the case, all right? when you have degree 1 type of problem, you usually have one solution. Not all of the time, but that's typically the case. All right? When you have degree 2 solutions, they usually, pardon me, a degree 2 equation, you have 2 solutions. Again, not all of the time, but that's the usual case. And it's kind of like that into infinity. So if you had a cubic equation, degree 3, expect 3 answers, even if you see the same answer more than once. All right, it's totally cool. All right, if you had degree 4, expect 4 answers, even if there's something being written more than once. Okay, that's graphing. All right, and it's a good way to be able to use your calculator as a skill. It's very important, but don't rely on it exclusively. Now, let me clean this up, and we'll discuss other methods. Okay. All right, let's talk about factoring. All right, if you want to examine this sheet, this is again a verbal instruction. What I would do if I were given a polynomial of a certain size. Any size, you start with pretty much the same method. If you have specifically 4 terms wide, 3 terms wide, 2 terms wide, these discuss the strategy that you might head in. Right, direction you might head in. Now, a little preliminary information to remind you. First of all, these mention polynomials. Polynomials are usually referred to as either monomials or binomials or trinomials. Beyond a trinomial, there's no specific label, right? Polynomial is a general way of referring to these things, right? Mono is specific, right? Binomial is specific, and trinomial is specific. But again, beyond something that is a trinomial, there's no quadrinomial. That would make logical sense, but there's no nomenclature for that. So what they usually will say is simply 4-term polynomial, right? If it has 4 terms, right? These have 3 terms, right? These have 2 terms, right? And this is just a term. Here's an example of each. If it's an algebraic expression, it's usually just a letter, so it'll be x. I like to put things in parentheses. It doesn't have to be that way, but to kind of encapsulate it. All right. X plus 2, right, is a binomial. It's 2 terms. Remember, terms is something that is separated by pluses or minuses in general. All right, x squared plus, that's very fancy, 2x plus 2, something like that. The problem that we had just done, right, was technically a trinomial on the right side, rather the left side, I should say, right? The side that wasn't 0, right? I moved it around. But it was 3 terms wide, right? So the expression from which the equation is made, remember expressions are the building block, and the equation is basically the house, the building, all right? That thing had 3 terms, right, on one side. So that one side, technically it was the left to begin with, was a trinomial, okay? As a generalization, right, this is what the building block would be, right? It's not always this complicated, but it would have these features. Plus or minus, and then a bunch of other ones. Something that's made of this basic shape, right, is a polynomial. Again, the only reason to know the name for anything, the label, is just to help distinguish it from some other specific thing. So, what are these features? X is the actual variable, all right? The thing sitting up in the front is the coefficient, right? The fancy way of saying number sitting in front of letter, all right? The condition that must be met to qualify as being a polynomial of any of these types is that it must be real, right? Meaning not a square root of a negative, no imaginary number, right? The other qualification is that the numeral that would be sitting here is a non-negative integer. That implies a lot, actually. Non-negative is a concise way of saying not negative. But what isn't negative? 0 is technically not negative. All right, and the positives are not negative. So to say non-negative is implying could be 0 or something higher than that. And then to say integer is implying that it's a whole number. All right, so no fraction sitting there. That's a different type of building block. Okay. All right. Let's do this and then we'll do some factoring. Okay. If you were going to solve this by factoring, uh, 4x squared minus 1 equals 7. Right? What you might try to do, good rule of thumb, is set one side to equal 0, right? It's would be closer to, what do you call it, standard form, right, of a quadratic equation. That's a preliminary step before you attempt to factor. And as this is given to you, it's not arranged that way. You notice that there's something other than 0 there. So here's where again we revisit the more basic techniques. We can rearrange the parts at will, all right, as long as we are careful. So I drew little tables a lot, right? If this is understood as being positive and I want to drag this over here for this purpose, then I just have to perform opposite operations. The opposite of subtracting, of adding, is subtracting, and I strategically write it underneath the thing I'm going to merge it with. All right. These will cancel. That leaves me with 0, which is what I want. And now I can mush together whatever I can. I have 4x squared, a negative and a negative. Same signs, you add them. All right, so you get a bigger negative, which is minus 8. Okay. Now here's where factoring comes in hand. In handy. All right. The go-to method, at least it may not work 100% of the time, but it's what you should definitely start with in terms of factoring. And I'm going to point to 2 pages. Here's the sort of verbal description. Any size polynomial, you want to try to factor in the style, for lack of a better expression, a monomial Gcf. And then you notice that there's this parentheses here. There's a monomial Gcf sitting on the outside of a parentheses, and then a simplified polynomial on the inside. Here is the same information, but as part of this overview diagram here that I made. This method over here. You're going to take your polynomial, that is just this that you see here that I'm tracing in with my finger, right? And break it up into 2 parts, right? So, just this chunk. This is factoring. This is a binomial because it has 2 terms. So I'm going to leave behind 2 voids on the inside of this parentheses. Again, essentially the chunks that you are breaking this into, you're factoring. are, technically it would be a monomial, but it would also be a greatest common factor. And this would be some leftover. That's not a technical term, but that's really what it is. It would still be a binomial, but it would be reduced somehow. It would be simplified, right? It's the leftover guts, if you will, after you've ripped something out of each one of them. The thing that in common, all right, the common factor, all right, and incidentally, if you remember, is what goes on the outside here. GCF, so greatest common factor, right, is the largest factor in common. What does that mean? Well, what are factors? Factors make products as opposed to multiples, right? Multiples are the products, factors make them. Right? So for example, if you were to list the factors of 4, you would see that they're 1 times 4 and 2 times 2. All right. And if you listed the factors of 8, which is what the other term here is, that would be 1 times 8 and 2 times 4. What is the largest factor that they have in common? It's 4. Incidentally, you don't have to write the number 2 twice, but I do because they're in pairs that they multiply. Well, this is made of 4. That sounds silly, right? Because it is 4 to begin with, but it's made of 4, and so is 8. So therefore, that's the thing that I could rip out of each one of these. Do they have a letter in common? They don't in this particular case. But if you were dealing with a letter, if you were looking for a greatest common factor of a variable, here's what you would do. If you're looking for the GCF of a letter, right, which is usually implying a monomial, essentially you want the highest, the lowest, it's ironic, the lowest power of each letter in common. And that's only if they have them in common. Again, this is in contrast to multiples. Multiples, ironically, least common multiple wants the highest power of anything, never mind that they're in common or not. All right? Well, GCF, you want the lowest power of a letter in common. In this case, this just has x squared, that doesn't have an x. So you can't rip an x and put it here because it's going to end up being left behind. It's not in common. So x squared remains here. All right. 4 times x squared makes this term. 4 times what, though, makes 8. 2. Incidentally, I put the sign here because it was already like that. Okay. This is probably as factored as you could go. Right? You should always start with this method, the GCF monomial factoring method, before you do something more complicated, right? As a rule of thumb, right? It doesn't always work 100% of the time, but it's one of the easier methods. And if you take the time to do it, and then maybe you coincidentally have to do something else after the fact, the numbers will be naturally a little bit smaller, so they'll be easier to work with. It's to your advantage always to check, is what I'm getting at. Right? It might be, since you see an x squared here and it's a binomial, the difference of 2 squares. But the thing about the difference of 2 squares, which is written here, is that both of these terms have to have an exponent of 2. And the number 2 that's sitting here doesn't. It's not that, if this was a 4 here, then yeah, you could write it as 2 squared because that equals 4. But it didn't factor that way. So pretty much, in terms of factoring, this is done. All right? Now you get to move on to the next method, the next part of this. Once you have set something equal to 0, as you dragged everything over to the opposite side, this is a preliminary step, and then you took the time to actually factor, and you finished. The last thing usually is to employ the zero product rule. The zero product rule is subscribing or attaching a label to something that you probably already take for granted. What is 0 times anything? 0, right? Well, it's a generalization. 0 times anything, we all understand intuitively, is equal to 0. What if I switch the position of these two things? Anything times 0 is still what? 0. What is 0 times 0? It's 0. That's the zero product rule in a nutshell. All right. Now, this is using an old-fashioned multiplication x and being somewhat verbose here. All right. What if instead of using a multiplication x, I just put things in parentheses and plotted them up against one another? It's still implied that they're being multiplied. Same thing here. Same thing here. Well, once something is factored, that's exactly what's happening here. So what you could do is assume that the thing, at least with a variable, this chunk unto itself does in fact equal to 0, and then rearrange the parts to see what the x would be. In the case of just a standard number 4 here, you can't do anything with it. If you really wanted to, you could divide out 4 and it would go away, right? And you'd realistically just be left with this. Anyhow, that 4 that doesn't have a letter attached to it cannot go any further. All right, so you could just divide it and it would end up being 0 anyway. What we have to do is now solve this smaller equation here. And I need the space for that. So I'm going to erase this and put some of this stuff above. Okay? I've got my 4x squared minus 2 equals 0. I've done myself a strategic favor and attempted to get rid of this 4, and that leaves me with just this term of this binomial is equal to 0. And now I'm going to try to, since it's completely factored, I'm going to try to solve this equation. All right. How do I do that? Well, there's another method that you're going to see on the sheet of quadratic equation methods, and it's called squaring, or square root property. This will be more or less step 4 in this case. Square root property. All right. Let me move this 2 from here to here first. If this is a minus, to move it to the opposite side is to add. They cancel, and then what am I left with? I'm left with x squared is equal to 2, because 0 plus 2 is 2. Once you've gotten it down to just one variable in the degree of 2, sitting all by its lonesome on this side, you can now employ essentially the opposite operation. You know how opposite operations are? The opposite of subtracting is adding, and the opposite of multiplying is dividing. Well, the opposite of squaring is square root. So if in theory you wanted to justify getting rid of this 2 here, you would employ the opposite operation. And then you would have that. Pick something up real quick. Alright, so this cancels this since they are opposite operations. That leaves you with the x. And then in theory, if you were to take the square root of 2, there could be a positive or a negative. All right? And since it happens to be a square root of an irrational number, 2, well, the square root of 2 is itself an irrational number, it's best left in that style. This square root of 2 symbol represents 1.41 some junk into infinity. So rather than write the decimal, which is probably our intuition, right? We've grown up with calculators, all right? We have to resist that temptation and just simply leave it as that, square root of 2, okay? Just remember to write the symbol plus or minus, right? The square root of positive 2 here, all right, can legitimately come from identical factors that are either both positive, 1.41 times 1.41, or negative 1.41 times negative 1.41. Identical factors is what a square root gives you. So that's the answer. Okay? And what we have accomplished is a lot of things at the same time. Let me refer back to the sheet again. We have basically factored and invoked the zero product rule. Because of the way that it worked out, we ended up doing this, the square root property, which again, if you're looking for a shape to sort of give you some direction, notice the breadth of this, the length of this side is rather stubby, right? It's just x squared. When you've gotten something to that shape, all right, you're going to try to use the square root property if you're degree 2 to begin with, right? It's for the reason that it's opposite operations. It's still kind of invoking the basic linear equation techniques. They never go away. They end up getting used last, is the bottom line, all right? But we call this the square root property, okay? So we've done graphing, we've done factoring in the zero product rule, and the square root property. It's a bit dark. All right, here's a larger problem. I don't want to beat a dead horse, but what I would do if you had a problem like this is still factoring, because it's worthy of us. X squared plus 8x plus 15 equals 0. Notice that this is already arranged, so we don't have to worry about it. We're still going to do the same things. We're going to make sure that something is set equal to 0. We're going to try to factor. All right, then we're going to try to use the zero product rule. And then we'll invoke some other older principle, or perhaps the square root property again. We'll see. All right. I'll bet at this point in your life, your math life, that you probably intuitively do this when you're factoring. And I don't want to tell you not to do that, because if you can go directly from the trinomial to its factored form, that's a blessing, all right? Usually when you have a trinomial, it ends up factoring into a binomial plus or minus a binomial here. And you just kind of stare at it and you tinker with these 4 parts and you figure it out, all right? And that's good. For something that's not too complicated, that the coefficient here would be 1, I would do that intuitively myself. In a couple of minutes, I'm going to show you a more sophisticated technique that accomplishes the same thing, but I'm reserving it for then, all right? If this is x squared, what's probably going to sit in the front of each of these? X and x, right? If you're trying to figure out what is going to sit here and here to compensate for 15, you have to consider the factors of 15, which is why it is good to know your multiplication tables by heart. All right, write them in pairs. All right, 1 and 15 and 3 and 5. of those two choices, which probably is going to produce the number 8, if you maybe add or if you maybe subtract, and in this case it would be adding 3 and 5, right? And I would say that for sure because there's no way in hell that if you try to add 1 and 15 or subtract it, that you're going to get the middle term 8, right? So you have this, x plus 3 and x plus 5, right? This is completely factored. So now we're going to use the zero product rule again. Right? Which is, I always do this as kind of like overkill, but I draw a little lightning bolt in between them and go, well, maybe this thing by itself is equal to 0. Maybe this thing by itself is equal to 0. Or maybe both of them. But I have to take those two situations, those two possibilities into consideration. All right, and then solve these equations independently. I get two answers, which is usually the norm anyway when I have a quadratic. So we go back now to linear technique. This is a linear equation. All right, so if you want to solve for x, you got to move 3. Justify that by doing opposite operations. The opposite of adding is subtracting both sides. X is equal to -3. All right. This situation, same technique, just using a different digit, 5. If this says plus 5, to justify moving it over equals, we do opposite operations, which is -5. These cancel, and then x is equal to -5. Here are our two solutions. Okay. All right. You should get in the habit, I don't do it, I admit, and I don't want to set a bad example for you. You should get in the habit of checking your solutions with the original equation to see that it balances. All right. I kind of personally reserve that process, unless somebody explicitly tells me to, for when I've done more complicated prep work. All right. Now let me show you something. Again, in this same packet, I gave you a page, 2 pages that are relevant. This one for right now. And this one, where again, this is some information that would be good in the long run to recognize. It makes, when you have internalized some information, you make more strategic decisions. You go, why does that number seem familiar? You'll see. If you recognize these numbers written in purple here, you might go, ooh, I could rewrite them in, as a square. All right. Let me do this over here. Just not to erase. If you were going to solve a problem like x squared minus 9 equals 0. Okay. Again, for the sake of strategy, look at how wide this is. Right? It's a binomial. Right? Again, for a verbal sort of cue, take a look at this sheet here. When you have a 2-term wide polynomial, which is really a binomial, right? The way that it might factor, not necessarily, is that it might be the difference of 2 squares, or it might be the sum of difference of 2 cubes. And it's pretty easy to decide which of those, cube or square, based upon the exponent, at least in the front. It can't be cubed, all right? Now, let's see, is it a difference? It is, because there's a subtraction symbol. The only other caveat is that the second term here has to also be written with an exponent of 2. The question is, can you write the number 9 with an exponent of 2? You can indeed. All right. And here's my reference again. The number 9 can be written as 3 squared. So if I just sort of take a little artistic license, right, and write it like that, it is more obvious that this is the difference of 2 squares, right? Which means that it conforms to a model that I might have memorized, or at least have a reference to refer to. How does the difference of 2 squares, this is the difference of 2 things that are being squared, how does that factor the factors are virtually identical when you're figuring out the four parts here, here, and here, except that there's no middle term. It's not a trinomial. So you have to have these opposite signs in order for there to be a cancellation effect if you were going to FOIL, and you're not going to do that. All right? Why? Because you're not multiplying, you're factoring. Factoring is dividing without consciously thinking about it. Anyhow, according to the model, and you have it on the sheet, it would be x and x, and then once we've identified what the base ought to be for 9, it's 3 and 3. And this is now completely factored. Right? And since it's set equal to 0, we can now invoke the zero product rule to solve it. Which is to say, well, maybe this thing by itself is equal to 0. Or maybe this thing by itself is equal to 0. We are now going back to, as we often will, all right, the more basic techniques of performing opposite operations to get to the answer. Just by moving these 3's over equals, we do the opposite operations. And in this case, you get x is equal to -3, and in this case, you get x is equal to +3. Sorry for the sloppiness. Okay, there's your two solutions. All right, again, you should check them, but I really didn't do anything too creative. The real time that you need to check for what they call extraneous solutions is if you multiply or divide by a letter, all right, or if you square something. Let me show you a factoring technique that is very useful. It takes a little bit of getting used to, and you may not have tried it before. I haven't seen anybody give it a name consistently between books, so I call it this myself. I call it, if I could just find the page, it would be great. What it looks like, AC product pairs and factoring by grouping. It's doing those two techniques at the same time. Factoring by grouping is a technique for when you have a 4-term wide polynomial, right? Which is not something that comes up that often, but it's pretty easy because you really only need to pay attention to 2 chunks at the same time rather than 3 things, all right? AC product pairs is referring to this model here where you have a coefficient in the front, let's just call it A as in anything, and a constant in the back, let's call it C as in constant. You purposely multiply those 2 numbers. Here's an example. We're still going to try to do this to set something equal to 0, factor, and then the zero product rule, but we have to factor, and that's the hard part. I do need this space, so I'm going to erase a little bit. The bottle's getting a little crummy here. I don't like to use the spray too much because the fumes actually are a little asphyxiating. If you see me pass out on the floor, you'll know why. It's the alcohol. I love math. Ah. One for you, one for me. One for you, one for me. All right, sure. Okay. I'm not a lover. I like coffee is what I like. Okay. So if you recognize this coefficient up in the front as A and this coefficient at the back as C, all right, and you multiply them together just to get through the process of factoring, then you might call this logically an AC product. All right. Products are made from factors. All right. Pairs of factors. I should, if I were a good guy and set a good example, go try the most basic method first, which is to factor out a monomial GCF. All right, I did neglect to do that. All right, it's not going to happen in this case because the greatest common factor of 4, 15, and 9 is just the number 1. All right, if I could rip a negative out of these, I would. That's the only other situation that I would attempt to go this route first. But I know already because I prepared. All right, it's not going to work. So forget that. I need the more sophisticated technique. What is 4 times 9? 36, right? 36 is a number that has quite a slew of factors. Always start with the easiest pair though, not necessarily what it came from, all right, but the number times 1. And I write them like this in pairs. 1 times 36, right? I put a comma just to separate them as factors, all right? It's even. So it's 2 and 18, all right, is another possibility. And 3 times 12, which I know because I memorized multiplication tables, all right. 4 times 9, which is what it came from. And then in theory, there's one other famous pair, right? 6 times 6. The reason that a person bothers to take the time to consider all of these is because what you're going to do in this case is you're going to split the middle term up into either a sum or a difference strategically. This is still sitting here, and this is still sitting here. And this is still equal to 0. But I need to figure out what's going here and here. And you might go, hey, wait a minute, buddy, all right? Why are you making this uglier than it was to begin with? Because as you'll see when I get it finished, it's going to be ironically easier. Just patience, right? Anyhow, if you may be added or you may be subtracted, what numbers make 15 out of these choices? And sometimes there's more than one choice, but you have to test them all to make sure that it works with the signs appropriately. All right? If you added 1 and 36, you're going to get 37. If you subtracted them, you get 35. No way is it going to be that. All right? If you added 2 and 18, you get 20, and if you subtract them, you get 16, which is just too short. All right? Not that. 3 and 12, that added would be 15, so that's a possibility, but let me just test the other ones. All right, 4 and 9, added 13, subtracted 5. All right, not gonna work. 6 and 6 added is 12, too short, and 6 minus 6 is even worse, it's 0. So the only possibility out of these compiled possibilities is realistically 3 and 12. So I'm going to put 12 here and 3 here. And since it had variable x attached to 15 to begin with, as an afterthought, I'm just going to put these x's here. Now I need to take the signs into consideration. These numbers here, which do make 15, all right, are smaller than the number. All right? It's not like one of them was larger. Since they're both smaller than this number, they would have to be added in order to make this number. All right? I have to remember integer rules for adding and subtracting and integer rules for multiplication a little bit later. All right? What combination causes something to add, make things get bigger? Same signs. Same signs cause adding, whether they're both negative, in which case you get a bigger negative, or if they're both positive, in which case you get a bigger positive. That's how I decide that this is a plus here and a plus here. Okay. Now your head might be spinning already, but stick with me, my story gets better. You'll see the benefit of this in a moment. I've taken this thing that was a trinomial. It was 3 terms wide, and yes, I've made it longer. It's now a 4-term wide polynomial, which is not called a quadrinomial, even though it should be, right? It would be logical at least, all right? What I've done is, basically I drew the model here. I've taken something 3 terms wide and I've made it 4 terms wide. The advantage to doing that, ironically, is that when you're trying to figure out how this factors, you don't have to pay attention to the whole thing at once. You can narrow your focus to just two things. So what I always do myself is, once I've got it rigged up like this, I purposely draw a little dashed line, like I'm putting blinders on myself, to go, just focus here, right? It's easier to do two things at once rather than three things at once, all right? And when in the case of 4 terms, that's really what you have to do, right? So I'm going to factor out a monomial GCF. What's the letter in common? X. When you want a GCF for a letter, you want the lower power. This is exponent of 2. This is an exponent of 1. So how much do they have in common? Just 1, right? As for the numbers, what are both 4 and 12 made out of? 4 itself. That's the GCF. This is a monomial GCF. 4 times what is itself? Technically 1. You could put a 1 here if you like, but it's superfluous. X times what would be x squared. That would be enough to put a second x here. 4 times what is 12? 3. The x is already accounted for, so no additional x. And the sign, if this is a positive times a positive, would make a positive. I'm now going to shift my focus to these two. And I'm going to go about the process the same way. I'm going to try this more basic method now of a monomial GCF and some leftover guts here. They don't have a letter in common, but if you examine the digits, they have some number in common. What are both 3 and 9 made out of? 3. I would say, if you're worried about a sign, start with the one that's here. Right? Sometimes you have to tinker with the signs as an afterthought, but I would always borrow whatever is sitting here, just to get started. All right? Now we figure out the leftovers here. 3 times what is 3x? X. 3 times what is 9? Positive 3. Now here's the deal. What you're hoping will happen just did. What you hope will happen in this process is that the junk sitting here and here are exactly the same. Because when that happens, this is the way it factors. The match gets its own parentheses, and this is my own way of referring to it. The left outs get their own parentheses. The match is more obvious, right? What is the thing that is matching here and here? It's x plus 3. What I refer to as the left outs, personally, it's very, very literal, right? These things, 4x and this positive 3 coincidentally here, are outside and they're on the left. They are left out, literally, right? Waka waka, right? So 4x plus 3. This is the completely factored version of this. And it is kind of involved because it involves a lot of steps, right? It involves a certain level of comfort with knowing your multiplication tables and factors of GCF, you know? But it's a very powerful method for factoring, right? And we'll get you to the answer eventually. Now that it is factored, you can go through the process of zero product rule, right? And you get what x is. I need the space, so I'm going to erase this. This is more or less the model, right? The match gets its own parentheses. Ironically, you only have to write it once in its factored form. Basically, a binomial rather than a monomial is the greatest common factor here, right? And it's on the inside. And then the leftover junk, the left outs, they get their own parentheses. That's this. Okay. this space. I'm going to just erase above this. Going on time. Now that we have this factored, you can invoke the zero product rule, which is to say, well, maybe this thing by itself is the zero factor, maybe this is. Maybe both of them. But in either case, we're going to go through the motions of solving. Alright. Move 3 by subtraction. X in theory is -3. That's one possibility. This one is a little bit uglier because it's 2 steps, but I'm going to move the 3 first. And that cancels this. You have 4x is equal to -3. How do I get rid of 4 if it's being multiplied? Divide. So this is the other one. X is equal to -3/4. Those are your 2 answers. Solutions, I should say. All right. Oh boy. I'm going to get a little more alcohol to clean my board. The trigger is getting a little sticky. Bear with me 1 second. Evaporated. If you have something that's higher than degree 2 rather, what you try to do when you have higher degree polynomials, equations, is try to take something and factor it into degree 2 and maybe a degree 1. Like if you had degree 3 to start with, you want to try to break it down into those factors, and then you can employ the quadratic techniques. Here's an example. All right, if you had something like this, -3x cubed minus 5x squared minus 2x equals 0. Again, it's already nicely written as set equal to 0. So as close to standard form as it could be. Now let's do this. Let's again go back to earlier technique for factoring. GCF method, which is to write something outside parentheses and write some shrunken leftovers on the inside of a parentheses. And since this is 3 terms wide, the leftovers would have to be the same width. Okay, this one isn't too bad because what is the obvious letter that they have in common? X, right? When you're trying to decide what the GCF that should be on the outside here is, it's going to be the lowest power. So if your choices are 3, 2, and 1, the most that they'll have in common across the board is just x to the first. So you're just going to put x. As for the digits, the factors of 3 are 1 and 3. The factors of 5 are 1 and 5. And the factors of 2 are 1 and 2. What's the GCF technically? 1, which I wouldn't bother writing under normal circumstances, but there is a small favor that you can do yourself. The lead coefficient is negative, so why not rip out a negative out of all of these things? I would make that a good rule of thumb, right? Do yourself the favor. Even if the GCF ends up being no bigger than 1, take the negative and stick it in the front, okay? Now we can figure out what these factor to. -1 times what is -3. Just regular 3. X to the first times what would be x cubed. X squared. And you keep going along. -1 times what is -5. Regular positive 5 it would have to be. Rules of integers for multiplication and division. Okay. X times 1, x to the first times what would be x squared. Another x to the first technically. The ones are optional, right? -1 times what is -2. Positive 2. X to the first is already accounting for the x that's here. So this is done as far as the Monomial Gcf method. And if I want to really make it concise, I can ditch this one and it's understood as being there. All right, as long as I keep the negative, it's all cool. All right, it's not wrong to put the 1 here, but it's superfluous. It doesn't have to be there. Okay, now this thing that I have here, I could try to factor a little bit further. And it's that much easier because I don't have to worry about a negative up in the front. I took care of that. I ripped it out. Rip, rip, rip. All right? So keep marching forward here. All right? This is going to be the A-C product pairs thing again. If this is your A and this is your C, then they form an AC product and they make factors. Well, they'll be factors. What's 2 times 3? 6. List the pairs of factors. Uh, 1 and 6 and 2 and 3. Of those choices, which makes positive 5? They both actually might make positive 5, so you have to explore the possibility, and sometimes you get a problem that's annoying that way. Ultimately, what you decide to use is based upon the sign here, all right? This would require subtraction, right, in order to make it into a 5. This would require addition in order to make it a 5. The other sign over here is a positive as well. So there's probably no subtraction involved in this. So if I'm going to take this middle term and break it up into a sum or a difference, it's probably going to be just adding. I have to write the stuff that is adjacent. There's this x here. There's this 3x squared. And there's this 2. And this is still equal to 0. But now I'm going to fill in the information here. This 5 is the result of 3x and 2x being combined. Again, it might seem weird that you're taking something that's pretty ugly to begin with and making it uglier. All right? But the reason that you're doing that, I have to put a positive 3 here, all right, is because once you have it as a 4-term wide polynomial, you ironically only need to pay attention to 2 chunks at the same time, which is easier than dealing with 3 at the same time. So, if I now narrow my focus while I'm factoring to just these 2 things, they have a letter in common, the most of which will be x. They have a number in common, that happens to be 3. 3 times what would be 3x squared? What's the extra thing that you need? An extra x, right? Would multiply to make it squared. 3x times what would be itself? Just plus 1. Now, since you've already seen this method in action, again, what you're hoping when you factor this one is that you get exactly the same junk as plus 1 here, right? That also kind of helps you if you're trying to figure out what the parts ought to be. You're looking to make sure that that's the case. All right, so let's see. This is still here, this is still here. and this is still here, and this is still here. I would borrow this positive. They have not a common letter, but a common numeral too. So you can figure out what goes here and what goes here. 2 times what is 2x? Just x. 2 times what is itself? Plus 1. What I was hoping would happen, did happen. The junk in here is exactly the same. What that means is that this thing here and here are a match. And they have to be exactly the same. They have to have the same terms, and they have to have the same signs. And they do, so thank God for that. All right? So what I'm going to do, I'm going to erase a little bit so I have the space, and write it up here. All right. The match gets its own parentheses. The left outs, that's my own way of referring to it personally, they get their own parentheses. So if the match is x plus 1, that's 1 parentheses. If the left outs here and here are 3x plus 2, then so be it. Then there's this hanger-on from earlier. So we have negative x. I'm going to give it its own little pocket. It doesn't have to have it, but I like it. This thing, x plus 1, and this thing, 3x plus 2, are all equal to 0. Which means in this case, we're going to have 3 factors of potentially 0. Dry enough. Okay, so maybe this thing is 0, maybe this thing is 0, maybe this thing is 0. All right, I got 3 equations. I got negative x might be the thing that equals 0. I got x plus 1 might be the thing that equals 0. I got 3x plus 2 might be the thing that equals 0, or all 3 of them simultaneously. These are going to require addition or subtraction. This one is just going to involve division, it looks like. All right. If this is a 1 here, and it's understood as being multiplied, if I want to justify taking negative 1 and introducing it to the opposite side here, I do so via opposite operations. The opposite of multiplying is dividing by negative 1. 0 divided by almost anything, 0 being itself the exception, you can't divide by 0. You end up with just 0. That's one possibility. In this case, moving 1 via subtraction gives you x is equal to negative 1. In this case, you subtract 2, and you get 3x is equal to negative 2, and then you divide by 3, and your third is negative 2/3. Okay. Notice, 3 distinct answers, solutions, because it was degree 3 to begin with. Okay? Sometimes you get the same number written twice, but it worked out beautifully. Okay. Now let's go back to the square root property. I know I touched upon it already, but it's worth mentioning again. To refer back to this sheet, all right, what you're going to see immediately is something that, not that you arrange it this way, but that it starts out mano y mano. All right, so you see one thing here on the right side or the left side, and another thing on the opposite side. All right, as long as it's degree 2, the opposite operation would be square root logically. So if you had, we'll try to get a couple of these in here. This is square root to solve. If you had x squared equals 8, right? No other features, right? Mano a mano, right? One-on-one, right? Then perform the opposite operation. The opposite of squaring is square root. If you've done it here, your hands are tied. You're obligated for the sake of algebra, for the balancing act that it is, very zen, right? You do it here, right? Just remind yourself, this known positive 8 here could come from a positive pair of factors or a negative pair of factors, and they tend to abbreviate that by stacking them, all right? This cancels this, all right? You're left with x, and now you have this, which is correct, all right? But here's where it gets a little bit more interesting. You can factor a radical. A radical is something that has one of those sort of division-esque sort of boxes wrapped around it, right? This is called the radical symbol. Whatever gobbledygook is on the inside here, I'm purposely scribbling because it could be anything, that gobbledygook is referred to as the Radic Hand. It's a fancy way of saying, and more sophisticated sounding than gobbledygook. It's the stuff on the inside, right? The type of radical is referred to as the index. Now, because square root is the OG concept of this, all right, they don't bother putting the symbol here. I feel they should, all right, just for the sake of clarity, but there would sometimes be a number written here, right? It's usually 3 or higher for a cube root, all right? Square root, they don't bother writing the 2, all right? But that 2 would be what the index is, all right? And this happens to be square root. All right? Now, how do you factor something like this? You factor it into 2 pieces, each of which would have to be under a radical. But don't pay attention to the radical so much as the number itself. All right? A couple of things I'm going to refer to here in the packet. 1. These squares, 1, 4, 9, 16, 25, 36, are good to know when you're trying to factor square root, right, of 8. Here is it from the perspective of square root, right? 1 could be written as 1 squared and so forth, right? When you're trying to factor, this is the ideal. You want to have one factor that is the highest perfect square possible, all right? So that it will be allowed to escape the radical, right? And then some leftover. The leftover technically could be a prime number or a composite number that would be inconvenient to bother with, to take it any further. You only know when you get there. 6, square root of 6 is an example of this. You could factor it into 2 and 3, but neither of them is a perfect square, so you wouldn't bother. All right. Anyhow, start by doing this. List some factors. And 8 is not too complicated. It's either 1 and 8 or it's 2 and 4. Of these 4 factors, which is a perfect square? It's on that sheet with the picture of the purple square. 1 is always a perfect square, and virtually everything is going to have that. But you want the highest available. 4 is the choice. What is it times 4 that gives you 8? Its partner here, 2. All right? Since 2 is not a perfect square, it's going to get stuck, left behind, inside the radical symbol. However, this, because it is a perfect square, the 4, will spit something out. All right? What's the square root of 4? 2. So that means that the factored version of this is the thing that escaped 2 times the thing that got left behind, square root of 2. And you still want to write plus or minus. All right. Now you might say to yourself, well, geez, why would I want to do that? Because these things are referred to as irrational numbers, right? Which means they're non-terminating and simultaneously non-repeating. There's no obvious pattern to them. So if you were going to get your calculator to give you the square root of 8, it would give you a high degree of precision, but it would never give you the entirety of it because it couldn't. If something is non-terminating, it goes into infinity, which means that if you wanted to use it, you'd have to round to somewhere, right? Just kind of arbitrary. So math people prefer to write things like this, simplified, which is synonymous with factored, because it preserves all of the infinity without having to chop it off, right? This would, if you involve this square root of 2 as part of some other calculation, no rounding involved then. And that means that you have an exact answer then, right? The irony about infinity is that we understand that this is the concept of something that goes on forever and ever, but in real life we have to chop it off at some point when we want to multiply or divide. That's why we have calculators, and we tend to make them do that for us, right? If you wanted to get the square root of 8, you would hit second and then x squared to get that symbol, and then put 8 in there, and it would give you that degree of precision, which is swell. But, all right, notice that it only goes up to the edge of your screen. It doesn't go into infinity. It can't. It'd be doing it for the rest of its life, your life, and never finish. All right, this is exactly the same answer. All right, 2 square root of 2 is still the same decimal. It's just using smaller numbers to express the same concept. That's why it's better. The eraser sometimes is no good. Here's a slightly more complicated problem. It's 2 steps. All right. We'll still be employing a square root at some point, but let's say hypothetically you had this. 4x squared plus 1 equals 7. This is similar to a problem we had from before, but you'll get a different answer because of the signs. All right. If we're going to go the route of square root property, right? That is, we're going to purposely try to isolate the thing that has the exponent of 2, then I'm going to move this over to here, all right? Why? So that it could be, like I said, a mano y mano. I think I'm spelling that right, and do forgive me if I've mispronounced it. Hand to hand, 1 to 1, right? One thing sitting here equals one thing sitting here rather than 2 things, all right? You might say, if you want to be funny, right? Mono, as opposed to mano, as in hand, right? All right. So subtract, minus 1, 4x squared equals 7 minus 1 is 6, all right? Move the 4. You do that via opposite operations, and now you're left with this. Once you've gotten it, again, mano a mano, right, down to 1 square and then a number on the opposite side, you can readily use the square root property as the alternative. So you have square root here, and then you have square root over the entire fraction. These are opposite operations, so they cancel. when you take a square root, it could come, as long as these things are both positive to begin with, all right, they are. The factors that make them would be either both positive factors or both negative factors to legit make a positive Radic hand. So I'm always going to have this plus minus stack here as an abbreviation. Now, the thing is, we can employ something called the quotient rule. The quotient rule says that if you're taking a fraction, and that's essentially what you have here, a square root of a fraction, you could break it up into its two parts, independently of one another. So what I'm getting at is that you could make this the square root of 6 by itself, and you could make this the square root of 4 by itself. Right? It would be to our advantage if we did do that, because at least one of them will escape the radical. As before, what's the square root of 4? 2. All right? At least that's out. Right? The preference in math, what you might say is good etiquette, like you stick your pinky in the air, sipping tea. Good etiquette of math means no radicals in a denominator. It's not really wrong, but for the sake of doing calculations by hand, it would be to our advantage not to have a radical in a denominator. So we still conform to that. The square root of 6, if you attempted to factor it, here's what would happen. Here's the factors of 6, 1 and 6 and 2 and 3. We want, again, ideally, a perfect square and then a leftover. A perfect square escapes the radical, but the only perfect square in this pile of factors of 6 is just 1. So if I put 1 here, I'd be stuck with 6, which isn't changing anything. You know, so I don't bother. Right? It's only something higher than 1. So you're stuck with the square root of 6. That means that this is the answer. X is equal to plus or minus the square root of 6 sitting on top of 2. Getting tired. All right. Completing the square method. Going back to this again. When you complete the square method, right, very often you end up square rooting at the end, right? Then there's the quadratic formula. We're going to do these two, and then we're going to move on to section 2.6, right? I could mention u substitution, but we'll see if there's time. Right? I don't think it's immediately imperative. All right, completing the square is basically taking something that is not factorable and making it factorable. Make something factorable. I'm not sure if that's really a word, but I think you know what I mean when I say that. Right? Capable of being factored, but it wasn't to begin with. It's a process. It's basically, you're going to have something written 3 terms, well, at least 2 terms. It's going to be a binomial on one side, but you want it set equal to 0. And then you're going to divide the middle by 2. And then you're going to square that quotient. All right, and then you're going to write it on both sides. Right. What you're basically creating is something called the perfect square trinomial. the perfect square trinomial, again, just to refer to my handout, is something that resembles this shape in the middle of this page. The perfect square trinomial is a trinomial, 3 terms wide. There's 2 different versions of it, the type that has a positive here and the type that has a negative here. The way it factors is that you have identical factors, right, which you could abbreviate. That's what's really the objective here. You take something that isn't factorable and you make it factorable. So if you had this, x squared minus 3x minus 5 equals 0. If you attempted to factor it, no matter how hard you try, you might go, all right, it's x and x because it's x squared. The factors of 5 are just 1 and 5. So if you put 1 and 5 here, there's no sign combination that's going to make 3. The best that you could do is make 6, or the best that you could do is make 4, but that's not 3. So it can't be factored. So what do you do instead? You employ completing the square method. Okay, I erased the number here. Minus. Okay. Let's see. Just to refer to this, the completing the square method, the way that you want the parts arranged is you want it to basically be a binomial on one side. Notice that there's just 2 terms here and then there's a constant on the opposite side. So it may have been given to you in a trinomial, but you're going to strategically move the 5. I'm going to take this 5 and plop it over here, right? Which means you would have to add it, and then you combine it if there was anything else there to begin with. It's just 0. So you have this. You have x squared minus 3x. I'm going to leave a void here on purpose. Equals 5, and then I'm going to leave another void. Completing the square is taking this middle thing here, minus 3, the middle coefficient, really. All right. And dividing it in half by 2, right? Stylistically, we would prefer to leave it like a fraction. So instead of putting colon with a line through it and minus 2, looks like a minus, we're going to use this line, right? And then we're going to square it and write it here and there, right? Remember what I've said to you, I think, the first day. You can get away with murder in math as long as you're consistent. So even though this probably seems a little bizarre if you've never seen it before at all, and go, geez, you know, I just ripping numbers out of nowhere and sticking them here and here. As long as you do it consistently to both sides of equals, you've balanced it and it's totally legit. So I'm going to take this 3/2 squared and just park it right here in its own little parentheses with an exponent. And then to make it legal, do exactly the same thing here. And I'm just going to, it's always 100% of the time going to be a positive and a positive. Okay? Now, it may not be too warm, fuzzy, and familiar, but what I've created in the process of doing this is I've purposely created something that is a perfect square trinomial on this side. This is now strategically a perfect square trinomial. All right. Which means if you want to, you could verify it by writing out these factors and foiling them. X squared would be an x and an x, and this 3/2 and 3/2 would be here and here. Of the 2 types of perfect square trinomial model that we have on the paper, this is the one that has the minus. So they're going to have identical minus here and here. If you foiled this, I guarantee you would get this back. Okay? We can abbreviate this though. There's two exactly of the same thing. So if I wanted to use an exponent, I could write this as, more concisely, one of these binomials, x minus 3 over 2, squared. Meanwhile, sitting over here, I'm going to do the actual arithmetic. When you square something, you square the fraction, you square the top and the bottom. So this is really 5 plus 9 over 4. If I go a little bit further and try to combine these, I'm just going to disguise 5 to look like a fraction. I'm then going to have to convert 5 over 1 into so many fourths, because that's the common denominator. 1 times 4 would be 4, 5 times 4 would be 20. If in theory I took 20 and added it to 9, it would give me this. 29 over 4. It's not a satisfying thing because we normally like a whole number as an answer, but that's the way it worked out. All right. The last thing is to invoke the square root property, which is why I put this arrow here. When you invoked the complete the square method, you end up doing the square root property anyhow. Okay. So I'm going to square root this, and then I'm going to square root this. This cancels that. And now I need the space again. That's one downside to working from home. I don't have board space at all. So what I'm left with is, hope this is dry enough, x minus 3 over 2, and on this side I got the square root of 29 over the square root of 4. The reason being, once you've taken the square root of a fraction, you can break it up into 2 pieces. All right? At least something will escape the radical. Basically, this is going to escape the radical as 2, because the square root of 4 is 2. Now, I'm going to move this over to here, where it has a friend, via opposite operations. And I'm going to attempt to combine these. This is plus or minus because of the square root. What am I left with? I'm basically left with this. 3 over 2, I'm going to write it more horizontal than vertical, plus or minus the square root of 29 over 2. If you write it that way, that's sufficient. If you write it this way, over a common denominator, this is also fine. Right? Because the square root of 29, the number 29, is not a perfect square, if you attempted to factor it, all right, you're not going to make any progress with it either, right? It's not going to escape the radical. 25 would, right? But even if you factor it, the only factors in 29 are 1 and 29. So it's a prime number, basically. You're stuck with it. Okay. The last of these methods for quadratics is the bazooka. It's really only appropriate to mention now, after having gone through the quadratic formula, completing the square method, because that's where it comes from. If you're going to solve via the quadratic formula, this is the formula. X is equal to negative b plus or minus the square root of b squared minus 4ac sitting on top of 2a. If you've ever wondered, well geez, where did that come from? It comes from taking this standard form of a quadratic equation and completing the square. In other words, if you went through the arduous process of taking the model for a standard form of a quadratic equation and manipulating it, moving it over so that it has a binomial on one side and a constant on the other, and then divide the middle term, and then square that, and then add it to both sides, and then attempt to factor, all right? You would basically get to this eventually. But this is a great tool if you have something that is also not factorable. This works for everything. Right? But you use it primarily when you can't factor, in lieu of completing the square, because it itself is the formula for, is created from it. Right? What you have to do is you have to have something that is in the standard form to begin with. So, what you will do is you will strategically take the coefficients and insert them in the formula in those places. Right? And then follow the order of operations. That order of operations would dictate that you deal with the inside of the radical first, which incidentally has a name. The inside of this is referred to as the discriminant. And the reason that it's called the discriminant is because it basically decides whether something is real or complex. Complex means that it has imaginary guts. Right? This implies that something is imaginary, like the square root of -1. What's the discriminant? It's just that much of the formula, b squared minus 4ac. Let's do an example, and I will finally shift gears over to the other section. Yeah, let's save that. Okay. All right. Wish my blue erased better. So say that you are given x squared plus x plus 2 is equal to 0. Right? The hard part would just be identifying what the coefficients are. Okay. If they're not written, what would you assume is the coefficient up in the front here? 1. And I would purposely write it there for the sake of plugging it in. Same thing here. This is A, this is B, this is C. So I'm going to superimpose it on the formula now. A is 1. I'm going to wrap a little parentheses around it. The reason why I do that is because sometimes there's a negative, and you have to make sure that if anything is being squared as you're inserting the value, that it would also be affected by a 2, the exponent of 2, if that were the case. Right? This is A, this is B, there's an A down here as well. The B is in 2 places as well. There's a 1 here and a 1 here. And the C is a positive 2. So you have a 2 here. Again, you must follow the order of operations, right? Which means that your focus should really be here on the discriminant. The inside guts. So you're going to square before you multiply and then subtract last. Right? That means that you do 1 squared is just 1. Right? Then you do the multiplication, which is 4 times 1 times 2, which is just 8. And then you attempt to subtract. What do you end up getting if you have positive 1 minus 8 in this order? You get a negative 7, which means you have an imaginary number here, which means that the answer is not real. It has a real component, but it would be more appropriately classified as a complex solution. This is out of the frame, sorry. A complex number has a real part usually and an imaginary part. Or you could say it just imaginary by itself. All right. And anyhow, this is what it boils down to. That's just the inside. If you have an imaginary number, what we do is we say, all right, we acknowledge that it's imaginary, and you can't combine it with the real stuff, unfortunately. So what we do is we put a little I out in front to go, this is imaginary, and then ditch the negative. This negative underneath the radical is signified by the I on the outside. Then we do this other part here on the top. And this is still plus or minus because of that. Negative 1. You see x is equal to negative 1 plus or minus I, just to acknowledge that it's a negative underneath the radical. 7. Sitting on top of 2 times 1, you do this after the fact, is just 2. If you like, you could write it like this, and this is sufficient. You can't add, do not add or subtract real and imaginary parts. They are not legally combined. The best you can do is sit them next to each other. If this was a real number, and in fact it came out of the radical, then you get added, right? But it didn't work out that way anyhow, right? You could write it like this, or you could write it like this. Right? The addition situation, the subtraction situation. Let's finally do section 2.6. I'm at 2 hours. I'll definitely try to get this done in 3. I'm losing my voice. I'm going to get a sip of water. I'll be right back. Okay. A little bit of grapefruit juice, actually. I count calories, so I'm just going to add this. Okay. 1175. Okay. Rock and roll here. Let's see. Section 2.6. You might be laughing to yourself. Really? 2.6 now? I'm sorry for the long. Because it's full too. This is how long they are. These classes. Solving other types. All right. These are strategies for solving other types of equations. Right. I'll give you sort of an overview here. Here's where we're at. Right. We have equations and techniques. If we were going to classify the type that we've dealt with for the most part, they're polynomials, if you wanted to be very precise. Polynomial-based equations. But the other types that you're going to see are the rational type. And I think on the first day, I did instruct you how to do this, but I'm going to revisit that. And then the radical type. And then there's another one that involves the absolute value. Okay. Now, the defining elements of these. The polynomial type has a couple of subcategories here. Let's see. We discussed on the first day the linear equations. And we just got through the quadratic equations. All those various techniques. How would you distinguish one from the other? All right. In a nutshell, linear equations have this as some component. They're no worse than x to the first. So I would employ the most basic techniques while I was doing this. Opposite operations, which means if you see addition, you subtract. If you see multiplication, you divide. Okay? That is always going to be true, and very often is the case. You may start out with more sophisticated techniques, and then eventually you come back to this. All right? The quadratics are no worse than degree 2. All right? And as you know, we just got through it. A lot of it is factoring. All right? Or the square root property. Right, or you can go straight for the bazooka, the quadratic formula. If not completing the square, if you really want to go that way. Right? And eventually, again, you come back to the more basic methods. Rational equations are the type that technically, and you haven't seen them this way this semester, but what they really are they're a negative exponent. Right. These two are non-negative exponents, right? And they're integers, right? Integers, which means that they're whole numbers with the sign. Whole number integers that are either 0 or positive. If you just make that one alteration and you put a negative here, all right, then it's a negative integer. Meaning it's still a whole number, all right? There's an abbreviation for this. When you see a negative, it's also kind of a situation where it's considered bad etiquette somehow. You could write it like this instead, all right? Once you move it from basically being on the top tier to the opposite, so the bottom, and you write it like that, the sign changes. All right. Negative exponents are this as an abbreviation. Right? There's a part of this packet again. There's a little list of methods for dealing with exponents. All right. This is the product rule, the power rule, the quotient rule, and so forth. Over here is what I'm alluding to. When you have a negative in the exponent, that's an abbreviation for making it a denominator. Okay? Now, what I had mentioned to you in the last class, how to deal with this, right, is basically to write an equivalent equation, one that doesn't look like this, one that eliminates denominators. How does it do that? Via the LCD. Okay. These are the type that are the new things, right, that have to be discussed today. All right. Just to give you some visual cues that you're dealing with one or the other, or versus any of these others. Basically, when you have a fraction as the exponent, right, as opposed to an integer, right, for an exponent. An integer is a whole number with a sign attached to it, right? A fraction is something that has a top and a bottom, right, as the exponent, right? Now here's the thing. There's two different notations here. Let me refer to this handout here. You can have something given to you in the obvious way that there's a fraction here. But if you take a look at this, let's say that you started out with something that had a fraction for an exponent. That's called rational notation, right? It's not to be confused with a rational equation. A rational equation is something that has a variable in the denominator. Variable in the denominator because of this situation. When you have something in rational notation, it's a style of writing which you can convert to radical notation, which is maybe the more familiar. Famously, if you have x to the 1/2, that is the same thing as saying the square root of x. They just don't bother to put the 1 here, and they don't bother to put the 2 here. They should. I think it would make things more clear. But these things are interchangeable. They're notations. They're styles of writing. Okay? Anyhow, what is the denominator? Is known as the index. And that is the more important of the two, because it tells you what type of radical that you're dealing with. The square root is normal for us, but it could also be a cube root. Anyhow, this diagram shows you where these parts would be, here and here. When you have something in the irrational style, you also have different ways that these are alternative ways of writing it. Because there's a product involved, and you see it here more obviously, and they're basically a fraction. You could write it in this arrangement, in which case it would end up looking like this. Or you could write it in this arrangement, in which case it would look like this. It is often more practical for your own sake to go this route if you're doing calculations by hand rather than with a calculator. Okay? Here's some other little particulars here. If you have the situation where you have a radical of the same index and the same inside exponent, but this is a variable here, not something that's known to be a +8 or a +7 or a +2. If it's a letter, you have to make this assumption, right? They have to be evens, both of these, for this to be the case, all right? But you have to make this assumption that the thing is not negative, because if it is negative, then it's imaginary. So we're trying to circumvent that. Okay. I'm going to explore the methods here because it's the meat, basically, of this entire lesson. Right? But I'm trying to explore the particulars of style here. All right. Absolute value. Absolute value is when you see something with those lines that look like this. That's known as the modulus symbol. right? And it basically means that you're going to have to write two equations, right? The modulus symbol is absolute value is a question of distance from 0. Right? When you take an absolute value of something. Direction is unimportant or less important. The absolute value is just distance from 0. All right? Don't care if it's left, don't care if it's right. So look for these cues. All right, you see probably nothing written in the case of the linear. X squared, you're dealing with a quadratic. We just had a whole 2 hours of explanation of that. A negative exponent would technically make this a variable in a denominator. If you have a fraction for an exponent, that's a genuine radical equation. It's just more or less disguised. And if you see an absolute value, it's kind of a dead giveaway because it's those lines. Okay. Moving on. Okay, quick review of just evaluating. If you had to evaluate, it's really just an arithmetic. So let's just say hypothetically you had this 2 to the third, h to 2/3 as an exponent. All right. What you want to do is take this and convert it from rational notation. I'm going to call it rad notation. Rat. It sounds so harsh, right? All right, and convert it to radical notation, which sounds so much more tubular, man. Okay, so make it not ratty, make it radical. All right. Okay. The denominator is the index, and this is the inside exponent here, at least to start with. So if you start with that symbol and you put the 8 on the inside, it's now a Radic Hand. Right? You would appropriately put the 3 here and the 2 here. All right, now, as I mentioned from this sheet, having done that, right, what you could do instead of writing it as I have right here is that it might be to your advantage to put this inside exponent on the outside. Legally speaking, you can, all right? And what the reason why that will be better, as you'll see, is this. If you actually did the multiplication here, you would have the cube root of 64, all right? Which is not impossible, all right? It actually is a perfect cube, all right? But if you strategically throw this outside so that it looks like this, you'd only have to deal with smaller numbers. What's the cube root of 8? There's another sheet in here where there's a reference, just to point to it. I don't want to drop my marker. But here you go. The cube roots are here. What's the cube root of 8? 2. All right. So if this is really 2 squared, what's 2 squared? That's 4, right? The cube root of 64 is the same answer. You're not going to screw it up. If you have a calculator, you can certainly get your calculator to do it. There's a button on your calculator labeled Math that does this, all right? If you turn on your calculator and you press Math, notice in the options you have cube root. And underneath that you have X, where you can decide what the index is. But the strategy of being able to manipulate like this is really the whole point of the exercise, right? You can get a machine to do almost anything for you, but it's unfortunately sparing you the experience, right? Which is not cool. Right? You want the experience. It's like, why join a gym if you're never going to use the equipment? I just came here because I wanted to hang out. All right, that's lame. Don't do that. All right, let's say that you did something a little bit more complicated. You had to evaluate 64 to the negative 1/3. This is a radical, it's something in rational notation to begin with. This is a fraction here, but it also has an obvious sign to it, right? So you have to bear in mind what changes will be made here. If you see a negative, all right, that means that this is really a denominator, all right? And once you've made that adjustment, this is now just a positive 1/3, right? It's just a very nice coincidence that this is already written here. If you were to convert something from rational notation into radical notation, this is exactly as it would look. And having a 1 here is basically innocuous. It doesn't really hurt it. All right. You could put it on the outside if you want, but it's not going to change much. It really is just asking you, what's the cube root of 64? And that is, you can use a reference, but it would end up making this 1/4. Okay. All right. Now let's do equations that have this. I'm gonna have to wash this. This is getting really bad. My eraser is really yucky. It works, thankfully, but it's like really needing a scrub. Especially the blue. I don't know what it is. Like blue, it writes nice, but it doesn't come off. Black is really the best. Right? It writes in nice contrast because of the white background, of course, but it goes on easy, it comes off easily. All right. Now, if you're going to solve a rational equation, it's going to have one of these in it, but it will be a variable. So you see this, 32. There's more than one way to do this, all right? Stemming from, I'm going to point at this once again, stemming from these options of how you write the original rational notation. But one of them is more practical than the other, and I would say that it's this one. So, not to waste time, all right, let's do this as a strategy. All right. When you have a fraction, right, raise the expression to the reciprocal power. That's the basic strategy here. In fact, I'll put an asterisk here because it's that important. Raise the expression to the reciprocal power. In other words, what's the reciprocal? It's the fraction flipped upside down, right? What is 5/4 flipped upside down? 4/5. Remember, you can get away with murder in math, even doing something like this, as long as you're consistent. So if you did this here, and you'll see why it's practical in a moment, do the exact same thing here. Okay. What happens when you multiply a fraction times its reciprocal? And basically, just as a reference, definitely need this one. This is the legal reason why I can get away with this. when you have just regular whole numbers as an exponent, where you have an exponent raised to an exponent, the operation going on here is actually multiplication. So for example, if you had x cubed raised to a 2, you would do 3 times 2 and get 6, right? Not to be confused with the product rule when the bases are being multiplied. In that case, you add the exponent. This is the power rule. This is the power rule, right? But simultaneously, what happens when you multiply a fraction times its reciprocal? It cancels, it goes to 1. That strategically is exactly what you want to happen. Strategically choosing to raise this to its reciprocal cancels it. All right. So you're just left with x. And now you have to deal with this. I would put this in radical notation now to deal with it. So if this is the index here, 5, that means that it's a 5th root, which is kind of weird. But it would be written like so. The index would be tucked in here, and this 4 would technically be on the inside, at least to start. What I was alluding to just a moment ago is that for your own practical, your own benefit, all right, if you're going to choose to write it this way or this way, go with this way because it's to your advantage. What that means is you could take this 4 and throw it out here and deal with it last. Legally speaking, it's totally fine. This is what it looks like. Why would you do that? Because although you're armed with a calculator, and you can make the calculator do numbers, certainly, this is what 2 times 2 times 2 times 2 times 2 is, 2 to the 5th, all right? That makes this x, the 5th root of 32 is just 2, all right? And if you raise it to the 4th as an afterthought, right, that makes the answer 16. And you don't have to worry about using a calculator. It helps to have some information already memorized, right? Multiplication tables especially. All right, but that's the gist. Okay. See something. Let me do that. All right, here's a slightly harder problem of the same type. What time is it? 2:30 almost. Okay. Dry, please. All right. If you had, let's say, rational expressions on, or you have radical expressions, but they're in the rational notation on opposing sides. This needs to get dry. All right. So let's say you had this: 3x to the 3/4 is equal to x to the 1/2. What you might try to do is pull some tricks, right? You might try to set this up so that it's set to equals 0, because then eventually you could factor. All right? I know it's not a quadratic per se, but maybe we can get it to be similar enough. All right, we'll see. Okay. if I were going to drag this from here to here, right, it's positive on this side, so if I dragged it over to the opposite side, it would look like this instead. Minus x to the 1/2 is equal to 0. Now I got to remind you of a couple of things, and that's what the handouts are for. All right. These two things are being subtracted. All right. So I can't really merge them together yet. All right. What I might be able to do is factor them, but before I do that, I want to adjust this. I'm going to try to basically write an equivalent fraction that is equivalent to 1/2 using the common denominator of 4. If I were to take 1/2 and sort of upgrade it to something over 4, that's going to change the appearance of the top. All right. What is it times 2 that would make 4? It would be multiplying by 2 naturally. If I did that to the bottom, for the sake of consistency, I must do the same thing to the top, and I would have 2 over 4. That means that I could make this look like so. 2/4 equals 0. Again, I can't combine these because this is a minus symbol in between them, right? But what I can do now is attempt to factor. I can factor this because they have a GCF, right? They have a letter in common. All right, and now thankfully they're the same index. So if I tear this out of here, and attempt to factor it like so, this will be the GCF. The letter in common is x. All right. The exponent that has to go here is not going to be either one of these, but something that is in the same index. Or actually, I can get away with using 2, I should say. I'm sorry. 2/4. Right. X times x is what will be needed here. And I'll figure out what the balance is. X to the 2/4 minus 1 accounts for what was already there. Remember when you multiply things that are the same base, and I'm going to point at this to make sure that this is clear. I know that there are no fractions here, but pay attention to the product rule specifically. When you multiply things that are the same base, you add the exponents. It's a little bit more complicated now because we're dealing with a fraction, but 3 plus 2, as in the example, is just 5. If I'm multiplying these two things to make that, and I would be if I factored, it would be a denominator of 4, but what would the numerator have to be to make 2 plus what equals 3? 1/4. Okay? So that's factored. It's a little arduous, but it did work. Okay. Now, here's what I will do. Since I've gotten it to that situation, now I can employ the zero product rule. This is one factor that, since it's butted up against what's in red here, it would be multiplied. That makes 0. So I have two equations. I have x to the 2/4. That might be equal to 0. And I have this one, x to the 1/4 minus 1 equals 0. This one is the easier one. Let me just make sure this is in the frame. I could pull the trick that I had established before, which is if I want to eliminate this 2/4, I can multiply by 4 over 2, it's reciprocal. And I would be obligated to do it to both sides. This would cancel, and it would leave me with just x, which is what I'm after. If you raise 0 to virtually any power, right, with the exception of 0 itself, all right, look at what you would have here if you expanded it. All right, it would be the square root of 0 to the 4th. Even, you know, if you raise 0 to the 4th, it's still going to be 0. Right. If I just neglect to write the 2 and just write it in a more standard way, what's the square root of 0? It's just 0. That's the answer as a result of dealing with this factor. Right. When I deal with this one, it's a little bit of extra work, but it's not impossible. The one thing I neglected to do was this 3 here, right? I'm sorry, there's a 3 here. So there's a 3 here. Okay. If I manipulate this one, I move 1 first by adding. They cancel. That leaves me with 3x to 1/4 is equal to 1. I would move the 3 first. I need the space, so I'm going to erase this over here. I got x is equal to 0 for the first one, and I'm doing this one. 3x to the 1/4 is equal to 1 now. I'm going to move 3. And that leaves me with x to the 1/4 is equal to 1/3. I'm going to pull the same trick. I'm going to raise this to its reciprocal, 4 over 1. If it's just a denominator of 1, you can just write 4. Right? But if it makes it more obvious, that's what happens. X to the first. And then this would technically be 4 over 1, which again would probably be just easier to leave it like that. Right? Having an index of 1 is not having a square root, right? When you raise a fraction to an exponent, both the top and the bottom are independently affected by the number here. So if it's 1 to the 4th, it's just 1. If it's 3 to the 4th, then that's 3 times 3 times 3 times 3, which is 81. This is the other number. 0 and 1 over 81. That's a hard one. I may have to get another paper towel for me. So. Here is kind of the normal situation. It's not written in rational notation. It's still a radical equation. But it's in radical notation. Suppose you had the square root of 15 minus 2x equals x. Okay. The basic gist of what we had from earlier. When you have linear equations, is that we use opposite operations. That will always be true. And if you know that much, you already can deal with this. But you have a couple of options. You can write it in this style if you like, right? As long as you understand that the inside guts would technically be raised to the first if you group them, and that the index of the square root would technically be 2, you could write it like this if you like. The easier thing to do, I think, is to just employ what you're familiar with, opposite operations. If I want to make this radical go away, then I have to square the whole thing. And if I do it to one side, I'm obligated to do it to the opposite side, in which case you would end up with this. This cancels this. All right, you do have to make certain assumptions. All right, be careful. But this is what you would end up with. All right. And now you see that you have a quadratic, which means that if you purposely drag all of this stuff over to here, that will leave a 0 behind, and then you will have x squared, opposite sign of 2x, plus 2x, opposite of a positive 15, minus 15, which is something that in theory is, you could factor it or attempt to, right? And then you'll get you to your 2 answers, right? If you went this route, it still looks like this for right now, right? You pulled the trick that we have been discussing, which is if you see an exponent that is a fraction, raise it to its reciprocal, and then do the same thing to the opposite side. When you have a 1, it's superfluous. You don't have to have a 1 for an index, you can just drop it and put 2. This would cancel, leaves you with an exponent of 1 overall, and that exposes the guts here. And this would simply be x squared. It would get you to the same place, it's just doing it in a different notation. This is a radical equation in rational notation. Style of writing. This is a radical equation in radical notation. That's this. Okay? When you factor this problem, to use the 0 product rule, it's going to be x and x, and it's going to be 5 and 3 to make 15. Just got to make sure that the signs are correct. It would be, in order to shrink, you're going to have to subtract. And you want a positive, the 5 has to be positive, and one of each causes subtraction, you'd have a minus here. This is going to be interesting for one other reason you'll see in a minute. When you solve this, using the 0 product rule, this is going to be x is equal to positive 3 in one case, if you solve for this factor, and negative 5 in the other case. One of these answers is going to be a dud, essentially, and it's not your fault. I'm going to purposely circle the correct answer, or the good answer. This is going to end up being the good answer. The work is fine, right? But this one is basically going to be the dud, even though it works out that way. It's a little bit out of the frame. Here's what happens, and you have to bear this in mind. I'll put this here. What sometimes arises when you're doing your work is that you end up with extraneous solutions. Essentially, bad answers. They're bad because they don't check. Right? They do not satisfy the original equation, which means they don't check correctly, right? The 3, if you stuck it in here, would make something that's totally cool. Here's what I'll do. I'm going to do this twice to prove the point. Right? if I plugged in a 3 here and a 3 here to verify that it's a solution, right, I'd follow the order of operations. I would have 15 minus 6. 15 minus 6 is 9. And the square root of 9 is 3. Does 3 equal 3? It does, which is why that one is copacetic. It's fine. If I did the other one, 15 minus 2x equals x, and I substituted negative 5, which is the way it would work out from factoring, and stuck a negative 5 in here and a negative 5 in here. This would be 15, double negative would be plus 10. 15 plus 5 would be 25, and this is under the square root, and this is equal to negative 5. All right? Here's what's going to be the problem. All right? I need the space, so I'm going to erase this. Even though the square root of 25, in theory, could come from identical factors of being one positive and one negative, when you're checking, you check with the principal square root only. The principal square root is the positive one. Okay? So once you have the, even though I know the options in theory exist for just the square root of 25, we must check with the principal square root, right? Which means that you have positive 5 here. In spite of their similarity, this is a negative, so they're not equal. All right? If you're wondering, well, geez, why do you have to be so rigid and do that to begin with? The reason is because of the original equation. Here's the original equation. This is something that is itself a square root. I'm going to purposely put the 2 here. And when I was dealing with it, I squared it, right? I did it to both sides, granted, but I squared it for the sake of eliminating. I brought this up a little bit earlier, but I'm going to point at it now. It's at the bottom of this page. When you have an even index and an exponent that are the same, all right, and you have a variable underneath the radical, all right, one has to assume that you have an absolute value, that this is a positive to begin with. All right. My squaring something would force the situation to be positive. All right. There happens to be a variable under here. All right. And you don't want that variable to cause this to be imaginary. Okay? Anyhow, it's a little perplexing, so if you don't want to think about it too much, and I'm probably not doing it any justice, convince yourself that when you check, you're going to use the principal square root only. Alright? Alright. Alright. Where do extraneous solutions come from? And this is why you should check, especially in those cases. You don't want this to be imaginary. Extraneous solutions arise from a couple of different situations. The first one is when you multiply or divide by a variable. When we solve rational equations, that is when there's a letter in the denominator. When we want to eliminate a denominator, a lot of times we end up multiplying by a variable. That's a situation that you have to be careful of. All right. The other situation is when you're squaring. All right. So if you do this, if you multiply or divide by a variable in the course of your calculation, or if you square in the course of your calculation for an equation, you're solving an equation, all right, check these, all right? One of them just may be extraneous, which means it does not satisfy the original equation when it checks. They do not check out, all right? All right? And when you do check, you exclusively want to check with the principal square root. Right, so the positive 5, all right, out of the square root 25. Okay. In a nutshell, extraneous solutions are duds. They're bad answers. Not your fault though, so don't get mad at yourself. That happens sometimes. You do everything right. All of your arithmetic is cool, all right, all of your algebra is flawless, and then you end up with a bad answer. It's not your fault. That's stubborn, isn't it? Okay. Times it. Okay. All right. Let me give you a look. Do that. All right, we're almost at the end here, but let me do this. All right, if you have a problem like this, where you have two radicals, so let's say that you have 2x plus 3, and then adjacent to it you have x minus 2, and this is equal to 4. All right, the trick to this is that you want to isolate one radical to either side. I prefer to isolate it on the left, personally. All right. When we get into absolute values later, absolute value, which is not this stuff, all right, will be similar. Similar process of isolating, all right, the unique feature. Markers are starting to die on me. Okay, so what does that mean? It means that I gotta manipulate the equation, all right? If I have two radicals on the left, I'm gonna plop one over here. So that means I'm gonna have this. 2x plus 3 is equal to 4 is in front. If it's positive here, it would be negative on the opposite side. So just to save space, I'm going to do like so. All right. And now that this is isolated, I'm going to pull the usual tricks. All right. If this is a square root and I want to eliminate the square root, I'm going to perform the opposite operation, really. Or I could write it in rational notation and multiply by the reciprocal would be 2 over 1. All right. Anyhow, this is faster, so I'm just going to simply do this. All right. And then I'm obligated to do that as well. This is going to be a little hairy, this problem, so it'll take me a couple of steps. But what will happen here is that this will cancel this, and you'll be left with 2x plus 3 equals. This thing is going to be duplicated, like a binomial. It is actually the perfect square trinomial. That's how it's going to work out, all right? I'm trying to save the board space, but if you want to see the minutia, it would be this. Okay. If you have something, even a binomial-esque looking thing, raised to an exponent of 2, there's 2 clones of it, if you will. For the sake of efficiency, which is a fancy way of saying laziness, right? But in a good way. let me point at something. When you have something that basically looks like this, two binomials sitting side by side, and I'm pointing at this one that has the negatives in it rather than the positives because this is negatives in it, right? It's not exactly the same, but it follows the same model, right? It's going to factor like this, right? I wrote it here. The middle is going to be twice the outside. So if you identify what the outside A and B value are, you could spare yourself a lot of foiling, right, by memorizing this stuff. If you're going to do it brute force, you'd have to foil, which is first, outside, inside, last. This times this times this. It's possible. It'll take a couple of steps, but it'll be a little messy. If you memorize the formula, right, or if you memorize the model that you have, you could predict what it will be without having to do the intricate work. Here's what will happen. This is my A. So according to the model, it should look like this. A is 4 in this problem. So therefore, it's 4 squared. All right? There happens to be an A here in the middle. That's a 4 there. This one is ugly, right? But this square root of x plus 2, or x minus 2, is b. I'm going to squeeze it in here and in here. X minus 2, x minus 2. The advantage to having the model on hand is that I don't have to do all the intricate work, which can get messy. The messier your handwriting is, the easier it is to make a mistake. All right, let's clean this up a little bit. 4 squared is 16. 2 times 4 is 8. It's 8 with this disgusting x minus 2 attached to it. This is a radical square root of x minus 2 that is also being squared. So the effect here is that this cancels this anyhow, which exposes the guts. You'll have plus x minus 2 left over. And since it happens to be positive, the parentheses are really not necessary. I do that as a precaution because sometimes you have to carry a negative. Right? Anyhow, continue to whittle it down before you start employing algebra again. Okay? You have some stuff on this side that are like terms. You have a 16, a regular number, and apparently a minus 2. So if you mesh them together, you got 14. And then you have this minus 8, minus 2, and then you have a hanger-on of x here. That is as much as you can do when you're trying to simplify just the right side. So at this point, what you might try to do is the same thing from before. Try to isolate the leftover radical to either side. I did it on the left before, now I'm going to do it on the right. What does that mean? It means that this 2x plus 3 that is left over here, I'm going to start bringing its buddies over to this side. One big table. I'm going to move the x and write it under here. It's technically 1x. On the same line, just to save space, I'm going to take what is essentially a positive 14 and move it and park it over here. And this cancels. And what I'm left with is this. I have this negative 8 still sitting here, and this x minus 2. Straightening this out, 2 minus 1 is just x. 3 and 14, one of each sign means that I actually subtract them to arrive at the digit. That means that I have 11, and it's a negative because of the sign of the larger magnitude. Okay, I need the space, so again, I'm going to erase a little bit. Duplicate this, I got x minus 11 equals negative 8 square root of 8 minus 2. This is not quite isolated yet because of that 8 there. So what I might do is, rather than divide it, I'm going to leave it alone because at least it's attached via multiplication. I wouldn't say that it is wrong to put the 8 over here, but it might make things uglier. It might be more trouble than it's worth in the process. As long as it's a coefficient, essentially, leave it alone. All right? How do you get rid of square roots? Via opposite operation, right? So if I square this entire thing, that would affect this, which is what I'm really after. But it would also affect this negative 8 here, which is great. As long as I do it to both sides, it's perfectly legal. All right? Now just to clean this up for the satisfaction, a negative 8 times a negative 8 is a 64. This tears the roof off of this x minus 2. This essentially cancels this. That leaves you with this x minus 2 behind. I'm putting it in parentheses because I'm going to have to distribute. Once you tear the roof off something and you leave the guts exposed, if there's a coefficient outside, you got to distribute. So you end up with 64x minus 2 times 64 is 128, and it happens to be minus. Now look what happened over here again. This is x minus 11 times x minus 11. It is again the perfect square trinomial, which again, you could FOIL it to figure out what the guts are going to be, but it's going to be x squared minus 2 times 11 times x plus 11 squared, according to the model for perfect square trinomial. And the result will be x squared minus 22 with an x attached to it, plus 11 squared is 121, and then there's this junk 64x minus 128. And now we have this, a quadratic, right? Because it's square root, it's x2. And you could do the same thing again. Pull the junk over. I'm going to add 128 to that. I think I may have got a sign lift somewhere. Let me just double check here. No, it's good. Okay. That's going to cancel on this side. If this is a positive 64, I'm going to subtract 64. I'm going to strategically park it underneath the thing that it most closely resembles, x. This cancels. That means that this entire other side is now 0. If you add this, it's 9, 1, that's 4 rather, and this is 2. And if you combine these two, you get 86, it looks like, x, and it's a negative. Same signs, add them, you keep the sign of the larger one, which is irrelevant, it's a bigger negative. And now you have this, yuck, right? This thing, believe it or not, that's left over here is factorable, all right? What you might try to do is, in a case like this, bring back something from arithmetic from a long time ago you might have a fuzzy memory about. Rules of divisibility. Something can be divided nicely. That is to say, no remainder. Right? If even, well, you could divide by 2 if even. This number 249 here, if I'm trying to figure out factors for this, it's going to be x and x, but these two factors are going to be harder. I'm trying to figure out what goes here and here. It's not even because it ends in a 9. All right? But there is a rule for 3. The 3 is you can divide nicely. It's divisible by 3 if the sum of the digits is also divisible by 3. 2 plus 4 plus 9 is 6 plus 9 is 15. 15 divided by 3 nicely? It does. That's 5, right? It's a whole number, no remainder, it's divisible. That means that this ugly thing, 249, can be divisible by 3. All right. 3 goes into 2, too small, goes into 24, exactly 8 times. 3 goes into 9, exactly 3 times. It's 83. 83 is one factor, 3 is the other. Now let's just verify that that makes the middle here. If you add 83 and 3, the things that multiply to make 249 apparently, they would make 86. We just got to make sure that the signs are right. They both have to be negative. Okay. If you go through the zero product rule here, this factor you would have x is equal to positive 3. And this factor here would be x is equal to positive 83. Those would be your two answers. It turns out that only 3 is correct. This 83, although the mathematics involved is correct, is extraneous when you check it. That's the hardest kind of a problem you can possibly do, right? Multi-step. Now let's get to absolute value. Some background information. An absolute value, I'm abbreviating, tells you distance from 0. That means that if you had an equation like this, the absolute value of the variable x is equal to 4. You'd have to take into consideration that what it was to begin with is that it might have been positive or it might have been negative. So what we do is we write two equations. We take it without the symbol. X equals 4. And then you write a second one, x equals 4. But you make this one negative, and you make that one positive. And those are your two solutions. It might, if the whole point of solving for x is to figure out what could x have been. Well, if it happens to be tucked inside absolute values, that's possible or that's possible, right? Every absolute value equation, you're going to write this and this, right? Two types, one that indicates that it's negative, one that indicates that it's positive. Okay. Here's a side note. Be suspicious. If your problem looks like this to begin with, there's no solution, right? In other words, if this is handed to you with these lines already drawn, notice down here they are not drawn, all right? And there's a negative here, don't do this problem. There's no solution. An absolute value will never give you a negative. The absolute value only tells you the distance from 0, nothing else. The sign is irrelevant to it, all right? Right. It's a trick question is what I'm getting at. here's what you'll see as an example. Black is dying. I used it too much. Oh, that's nice. Let's put that in there. Hopefully that will recover. If you have x plus 6 equals 10, as I was alluding to before, you want to isolate either a radical or an absolute value to one side or the other. It really doesn't matter which, as long as it's one of them. So drag 6 over to here. Minus 6, minus 6. Then you have coincidentally 4 again. Right? Then you break it up. Right? This could have been a negative or a positive inside. So how do you account for that? You go x is equal to negative 4 or x is equal to positive 4. And there's your two answers. Let's make sure that's dry. 3 hours. Let's say you had this one. (3x minus 5 minus 4 equals 6). All right. Move 4. And if there was a coefficient here, you'd do the same thing as well. All right. You want to isolate first. All right. Split second. These cancel. You're left with the isolated absolute value. And then this equals to 10. Right? Now that this is isolated, you're going to split this in two. So you're going to take into consideration, geez, I died in the middle of it. Gave up the ghost. All right. That's kind of okay. 3x minus 5. 3x, is it just this place here? I think that's the end of that. I'm going to throw this out. That'll last forever. Okay. This one works. Okay. No, that wasn't much fun. Okay. That's okay. All right. You have the guts of this now exposed. And what do they equal? 10 and 10. On this side, you're going to take into consideration that it might have been a negative, and in this case, you're going to pretend it's a positive. And then you go through the motions, right? Add 5, add 5. 3x is equal to negative 5, divide by 3. One possibility is that x is equal to negative 5/3. Again, don't be upset by the fact that it's an improper fraction. That's actually preferred over a mixed number. Over a mixed number, and sorry, I'm getting a frog in my throat. A mixed number is practical when you're talking to another person, but it's not the preference in algebra or in pre-calc. You leave things as improper fractions, just simplified. All right, this one. Plus 5, plus 5, you get 3x is equal to 15 in this case, divide by 3. X is equal to 5. Two solutions. For absolute values, expect two solutions, right? Normally, right? There is a potential, like if you have a problem that if you have an absolute value of equal to 0, there's only one answer. Alright, but that's if it was equal to 0. Alright. If you have it equal to a negative, there's no solution. Okay, two more things. Let me review rational equations, that is the things with denominators, because those are kind of difficult. And incidentally, if you had a weird situation where you had two absolute values in the same problem, and I don't think that's going to come up, but if you did, you isolate one to the left or to the right. That's always stubborn. Blue marker, he's such a good marker, except when you want to erase. Here again is just a review. A rational equation. The basic gist here, again, is that you write equivalence equations using the LCD. This is fading out too, huh? When it comes to the LCD, right? The lowest common denominator is the least common multiple of denominators. There's finding it of the coefficients, and there's finding it for the algebraic expressions. Oh boy, I'm having no luck today. One dot after another. Okay. You could do this the old-fashioned way, which is to list multiples. What is on the board? I just thought I dried it, but apparently I didn't. Okay. Yeah. Okay. You can list multiples, or you can go through this sequence with your calculator. You hit the math button, and then scroll over to where it says num, and go down the list. There's this function, LCM, which you'll have to put in, a comma. This is a dud. All right. The basic gist for algebraic expressions, wow, that writes so much better. I didn't dry it very well, I guess. Okay. The basic gist for these, let's make sure that's dry, okay, is you want the highest available power of each unique base. And it's as best I can summarize. Okay? So if you had a problem that was pretty ugly, let's say that you had something that looked like this. Negative 4x over x minus 1. plus 4 over x plus 1 is equal to negative 8 over x squared minus 1. All right. Do yourself a favor and factor where you can. So try to factor first. This, the most that you can do if you were going to factor it, is simply write it in parentheses. And now it's a factor, it's a binomial factor. Same thing here. This one, x squared minus 1, is the difference of two squares. Because the number 1 can be written as something squared and it's not changing its value. The exponents of 2, this is a subtraction symbol. The way it would factor would be exactly like this. Okay. The advantage to taking the time to do that is that you will have an easier time of identifying this. You don't have any coefficients here that are being multiplied. So you don't need to go through this process. Right? Of either listing the old-fashioned way and looking at the multiples, right? Or going through the function. What you need to do is to include the highest available power of each unique base. These happen to be bases that are binomial, so be it. This is an exponent of 1, an exponent of 1, and each one of these is an exponent of 1. Right? If I want to write an equivalent equation without denominators, that's going to eliminate them. Basically, I'm going to take this entire thing and I'm going to multiply by the LCD. This is going to eliminate the denominators. Okay, so the common denominator is one of these each unique. This x squared minus 1 is really these two things, all right, that happen to be here and here. So that's the LCD. It covers all bases. So I need the space, but what I'm going to squeak in here is that LCD. X plus 1, x minus 1. Remember what I'm fond of saying. You can get away with murder in math as long as you're consistent. So if you apply this to this first term, do it to the second one, do it over the equals to the third, and everything is fair and square. The effect of multiplying this times this denominator is that this goes away. What it will leave is the negative 4x that's there and the one of these that wouldn't have been related. Right? So if I canceled out x minus 1, it would cancel out here as well. That would leave me with x plus 1. If I applied these two again to this one, cancels out this one. What does it leave behind? Plus 4. And then the one that didn't match, so x minus 1. This one, the payoff is great. You know, it's both of these two simultaneously, which means that. What does it leave me with? Minus 8. Okay, there's a lot of cleaning up to do, but it's not too arduous, right? Distribute, 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 distribute. Negative 4x squared minus 4x plus 4x minus 4 equals 8. There's a lot of cancellation here, gratefully. All right, these two things in the middle are like terms of opposite sign. All right. They also have the same coefficient, so they completely go away. That leaves you with minus 4x squared minus 4 equals negative 8. Pardon me, it is negative 8. Okay. Now you have a couple of options, but probably the easiest thing to do is try to pull the zero product rule stuff. So I'm going to bring this 8 over here. All right, so I'm going to add 8, cancel, add 8. This is equal to 0, so maybe it's factorable. These things are, let's see, positive 4 and negative 4x squared. That's going to be factored. I need the space, so I'm going to erase a little bit. 4x squared plus 4 is equal to 0. You can factor it. They're both made of the number 4, evidently. I would take the negative as well. Negative 4 times x squared would be negative 4x. Negative 4 times 1 would be 4. The sign would have to be minus. And what you coincidentally get here is something that is still factorable as the difference of 2 squares. Which means that this x squared minus 1, which could be written like that, is x minus 1, x plus 1 equals 0. And there's still this hanger on here. Okay. If you go through the motions now, you could go ahead and get rid of that 4 right away by dividing. And you're just left with this, x minus 1, x plus 1 equals 0 divided by anything except 0 would be 0. These two, according to the zero product rule, would be either this or this. Which means that you'd end up with x plus 1 here and x minus 1 here. Now I would be a good sport and check these for extraneous solutions, but I'm going to tell you right now, this is so vexing. When you go back and check these two, yes, in spite of all of the work involved here, neither of these works. They're both extraneous. And it's not anybody's fault, all right? Where did it come from? Extraneous solutions come from either squaring or multiplying or dividing by a variable. You had to do that in this case. Well, that would probably be the easiest thing to do. But what it exposed is that there's no solution. That's not your fault, right? Nonetheless, the experience, the mental exercise that is involved was worth it, right? So don't ever feel bad about going through all the trouble and then getting a dud or 2 in this case. Not your fault, right? They're both extraneous when you check them. Here is the absolute last thing. It's a special technique, which would be useful, I would guess, in calculus. Yes, definitely. All right. This is a special technique. Right? It's called U substitution. Right? Basically, it's a way of rewriting a problem so as not to be, oh yeah, here we go again with this. Is it okay over here? Yeah. I don't know what's on the board all of a sudden. Not to be distracted like I am now. It's more or less just hiding or concealing information so that you don't get bogged down when you're doing the intricate work. Alright. There are some criteria, alright, when to use. When you have a polynomial in descending order, means that the degrees go down. Alright. You have to have a polynomial in descending order. Degrees go down. Okay? when the exponents have the same bases. When the third term is a constant, which implies that this is a trinomial. And then lastly, when the degree of the first is double the degree of the second. These four criteria must be met in order to employ this. Here's the example that I will give you that I promise will work. I'll erase this after I show you. 3x to the fourth minus 2x squared minus 1 equals 0. Let's certify that it is these four criteria. All right, first of all, is this a polynomial in descending order? If it's a polynomial, it's made of this building block. A positive, or technically 0, for the exponent. They're all positive. It is in descending order. The exponents diminish out of existence. The degrees go down. So that's fine. It's a polynomial in descending order. The exponents have the same bases. That's a base x. That's a base x. So that's cool. The third term is a constant. That's just a regular 1. Very good. Degree of the first is double degree of the second. This is the first degree. This is the second degree. 4 is double the second. 4 is double this thing. So that fits all four criteria. What we're going to do is now this. We're going to take x squared, this thing here, and call it u instead. Now I need to erase. So, if I do that, this is the original problem, I'm just duplicating it over here, make sure that my thing isn't burning out yet. And I'm just going to superimpose this. I'm saying x squared is really u. That means that if I wanted to rewrite x to the fourth, right, if x squared equals u, then that means that this would be u squared. And you would have this instead. How come? Because u squared would be x squared squared. U squared would be x squared, because that's what it represents. If you squared it, it would be 4. In this version of the equation, you don't get bogged down with intricate details. You could do this also if this was a binomial here and here. This is factorable. All right, I'll show you AC product pairs. A and C is 3. There's only 2 factors, 1 and 3, thankfully. This, if I split it into a sum or a difference, would be, let's just make it what it is, 3u and 1u, negative and a positive. A negative 3 to make it a negative 2. That's factoring by grouping. If I now pay attention to just these two factors, they're both made of a u, they're both made of a 3. 3u times u is 3u squared, 3u times -1 is itself. These, pull out the positive here. 1 times u is u, 1 times -1 is itself. What I was hoping would happen, did. This matches this. So that is u minus 1, and the left outs. 3u plus 1 equals 0. I would go through the process of solving it before I reverse the substitution. I have to do that eventually. I need the space though. Time wasted doing this. Erasing and erasing and erasing. I don't have a full-size board. That we'll have to do. This is possibly equal to 0 because of the zero product rule. This is equal to 0 according to the zero product rule. In this case, crikey, will you please dry faster? Yep, still a problem. That's why I'm running my markers. Plus 1, u is equal to 1. Minus 1, 3u is equal to -1 divided by 3. U is equal to 1. U is equal to -1/3. Okay, now I'm going to reverse. What is on the board? Right's over here. Doesn't right over there as well. Okay. I'm going to reverse the substitution. Now it works great. Okay. U is x squared. So I'm going to put an x squared here. U is x squared. Let's go through the motions now. How do I get rid of something being squared? You square root it, do it to both sides. This cancels this. X is equal to plus or minus 1. That's one possibility. This one would be the same exact process to do that. But because you would end up with a negative here, it's not drying fast enough. This is going to be imaginary. So the way that I'm going to compensate is by putting an I out in front of this. It's plus or minus, but x would be equal to plus or minus the imaginary number that is the square root of 1/3. There's no simplifying it, you kind of stuck with it. Okay? And that's that. Notice that it was degree 4 to start with. 2 answers and technically another 2 answers. Those are 4 answers. All right. Thank you for sticking with me for 3 hours and 38 minutes. All right. Try section 2.5 and 2.6 in my open math. All right. What I'm going to do is record next Thursday that assignment. All right. I'm going to record on Tuesday 2.1 and 2.2, which is already in play. All right. Make sure that you get it. My open math account. Okay. Thank you guys. All right. I try to be as thorough as possible. Definitely print out this packet. It has a lot of references. All right. And if you need to, watch the video while you're doing your work. Okay. All right. Take care. Be careful out there. I'll see you on Tuesday.